Mic check, hot, hot, not too hot, gravy.
Okay, everybody, we're going to go ahead and get started. Welcome to Cassandra Summit. I hope you enjoyed the keynotes. And I'm going to be talking about something that a lot of people are talking about these days, retrieval augmented generation, AI, and how to use Bedrock with Astra to create a question and answer session. So this is me. I'm a developer advocate at DataStax, Kirsten Hunter. I wrote a book called Irresistible APIs. I'm very much about the developer experience, making sure that there's no speed bumps when you get started on technology until you actually get to where you want to get. So what will this talk cover? I'm going to use Romeo and Juliet as scene Act 5, Scene 3, which is where all the dying happens. And we're going to load that into our vector database, and then we're going to ask questions using prompt engineering. And I'm going to do this in a very easy way with Amazon Bedrock. You will notice that I have Romeo and Astra instead of Romeo and Juliet, and that is because when you take one of the LLM models, it will cheat. If you say, only use the documents that I have, how did Juliet die? It'll cheat. It'll look at the huge upload that it had from the web, and it'll give you the answer based on that. So I changed her name to Astra because Romeo and Astra is not a thing. It has to use the documents that I'm giving it. I'll talk a little bit about Amazon Bedrock, which is how we're using, we're creating the embeddings and the completions. I'll talk a little bit about DataStax Astra, which is a vector database. It is Cassandra. We have actually introduced vector search to the database. That's going to be in Cassandra 5. Right now it's just in Astra, but we're pushing it to the core so that you'll be able to use that going forward with your Cassandra instances. We'll talk a little bit about how a vector database works so that we understand that. I'll go over the process of the demo, and then we'll just do the demo. I'm going to show you how I'm going to use a Jupyter notebook and walk through the steps necessary to upload that information with the embeddings, create a query embedding, and then run it through LLM for a nice result. So I mentioned what the demo is. Again, we have Romeo and Juliet, except we're using Romeo and Astra. What we're building is a sample RAG application to demonstrate the process. Uploading the documents using embeddings. We're using the Titan embeddings from Amazon. Create a query using the same Titan embedding. Retrieve the similar documents, and then use a prompt to clean up that answer and turn it into natural language. So Astra. Astra is a real-time vector database. It's not just a vector database. It is a fully fledged Cassandra database that also knows how to do vector search. So you can put all of your stuff in there, not just your vector stuff, and it can all be maintained in the same database. One of the things that is important is that it indexes in real time. So one of our competitors, the queries slow down significantly when it's in the process of indexing, and it has to go sort of offline a little bit for indexing, and so that makes things slow. Astra does everything in real time. The reads and writes are real time, and so you get that responsiveness even when it's in the process of doing indexing. So how does a vector database work? How many of you are familiar with how vector database works? Okay. So we create a vector store, and the vector store allows you to have documents, and basically the embedding is like an address in space. Like where does this document live in my document space, right? And so it's a very complicated address. If you're using OpenAI, for instance, it's 1,376 dimensions. So it's a very precise address in your place, and so that's what you do. You create the vector store, you populate it with those documents and those embeddings, and then when you have a query, you send the query through the same embedding to find out what its address is, and then it goes into the database and figures out what's near it, right? So we're talking, this is much closer to semantic search than the searches that we normally do on databases, which have very specific keys and value pairs. So it's pretty sexy. I mean, I've loved semantic search forever. Okay, so Amazon Bedrock is a managed service for AI foundation models. There are tons of AI foundation models, more coming all the time. What Bedrock does is it lets you sort of use their interface to use those models, so you don't have to go set up those models separately. You set up your Bedrock, and then you choose the model that you want to use. This example, we're doing Amazon Titan embeddings and the Anthropic Claude 2 model as the LLM. Models can be changed and switched out as needed, and that's really important because when I first did this, I used one of the other completion engines, different than the one that we chose to use, the Claude one. And I said, in 20 to 50 words, tell me how Juliet died in Romeo and Juliet. And it said, stabbed. Okay, that wasn't 20 to 50 words. You know, prompt engineering is really tough. But if I use OpenAI, it says, oh, well, she took a potion to make her look dead, and then Romeo came and thought she was dead, and so he killed himself, and then she woke up and stabbed herself, right? That's a good answer, right? But different models behave differently. Okay, so the steps that we're going to follow for the demo. I'm going to set up my Python environment. We're just going to go through a simple Jupyter notebook for this. So I'm going to set up the Python environment, the credentials, and everything that I need. I'm going to create a vector store in Astra. I'm going to create an embedding for the query to retrieve similar documents and pass it through the LLM. This will all make sense when we look at the notebook. But for now, does anybody have any questions on kind of the vector store stuff and how it works? Nope? Okay. So let me show you this sort of with pictures. So this is retrieval augmented generation. And so we give it the context, the tasks, the roles in the persona, and the constraints. So we have our data on the left-hand side, and we split it into documents. And then the documents go through the embeddings API, and then they get put into the vector database. And then the prompt goes through the same embeddings API to create that embedding so that it can tell the vector store, I want things that are similar to this. And then it sends out the documents for you. And then when you're doing RAG, you take those documents, and what we'll do is we're going to take the documents we get back and then have the LLM massage it until it gives you a good answer.
Can we use the word space and dimension interchangeably?
I'm sorry, what?
The word space and dimension, can that be used interchangeably?
The dimension is kind of the address, and the space is kind of the whole thing. All right, so I have a demo. And of course, there are demo daemons, so if it doesn't work, then I'm going to put this in the chat for the talk so you guys can play with it too. Okay, so I'm going to set up my Python environment. And I'm installing, what's really important here is Cass.io. That is our library for using LangChain, Llama Index, OpenAI. We've actually made it work for all of those things. And it's just going to take some time because I'm standing up here and y'all can watch it. I'm going to say that this is not the fastest internet I've ever encountered. So we're using, so you see we have Cassio and LangChain, Cass.io. We have Botto 3 and Botto Core. Those are the ways to interface with the AWS system. And then there's a few things that are necessary for the particular example that we're showing. And this should be done any moment now. That's what you get for doing a live demo. Okay, still working. The nice thing about this is that you can ask all sorts of different questions about Romeo and Astra. And you can see here, with the lang chain embeddings, we're importing at Bedrock embeddings. That's how we're going to access the embeddings that we want to use. So we're basically using lang chain as a adapter to Bedrock. LangChain is just a really fantastic way to get the models that you want to use and use them. All right, that's done. Yoo-hoo. Okay. This is a tricky one. Yes, that's right. I send it to myself in Slack. Okay, and then Astra CS. So this is the token that you need for using Astra. And the other piece of information is the DB ID, because you might have a different, some different databases, and they might be named the same, which is something that we want to not encourage, but this way you're using the actual ID for the database. Okay. Now, the moment of truth. Okay. I may just have to talk you through what it's going to do if it's not happy with my token. Thank you all for your patience. Oh, that's better. Okay, so those warnings are known. There are some things in the back end. Cass.io is going to get rid of them very shortly, but we are successful. So now I need to do my AWS ID. I never do easy demos. Okay. Probably should have set this up ahead of time, but I wanted to be honest about what is required. And this is actually out there. You can play with it yourself as well. Okay. Let's see, session token. Session token is really the reason why I can't set this up ahead of time, because it refreshes like every half hour. All right, let's see if we succeeded at that. So what I'm doing here is I'm setting up the Bedrock runtime, and then I'm using the embeddings, and this is where I'm setting the model that I have. So I can do any of the models that they have for Bedrock right there. I can switch them out. I can change them. It's all really easy. Okay, so I've just created a vector store named Shakespeare Act 5. I'm going to grab the document that has the lines from that particular act and scene. And then we're going to go ahead and it's going to take a couple minutes to add the 321 documents. So there's 321 lines. So what I've broken the play down into lines. Each line is its own document. And then it has the embedding. So it's just basic Python that we're doing here to add this. And it's going to say done in just a moment. But let's go ahead and look at the prompt while we're waiting. So we're telling it, as a human, use the following pieces of context to provide a concise answer to the question at the end. If you don't know the answer, just say that you don't know. Don't try to make up an answer. That last part is almost always what you want if you're doing retrieval augmented generation, because you do not want it to take the whole internet as of 3 years ago and give the answer based on that. You want it to give the answer based on the documents that you put in. Okay, so we did the prompt. And so we're using Anthropic Claude. It actually behaves much better than the Titan completion for our purposes, right? So you may find out that actually Titan works great for what you want to do, but for what we wanted to do, we ended up liking Claude better. And then this is how we're going to answer the question. We're going to create an embedding. We're going to stick it in there. And then by evoking the model. And then we're going to give the answer. So let's see what we get. To go. That one's done. Excellent. Okay, so what do we get? Based on the provided context, it seems that Astor, Tybalt, and Romeo all die in the story. True. Specifically, the lines mention that Astor was found dead and bleeding. Tybalt had an untimely death. Romeo was also found dead. So that's a pretty good answer, right? Who died in the play? And this one shows you, these are the lines that it found. There's duplicates because I didn't clear out the database before I did it this time, so we got some duplicates. But it takes the 15 lines that it got that were in the region of who died in the play, and so it did the correct thing. So does anybody have any questions about how this all works? So I have an Astra database that's running, and that's what I used the credentials to get. I also have AWS access to using Bedrock. This is new. It's something that you probably have to add to your roles in AWS in order to make it work correctly. I would love it if people played with this. I will put a link to it in the session notes, and you're welcome to give me feedback on it if it works for you, if it doesn't work for you, if you have questions about how to ask kind of different answers. Yes? I'm sorry, what?
Would this work with regular Cassandra?
So Cassandra 5.0, which is in beta, you can actually get a Docker image of Cassandra 5, and it has this vector search in it, and it will work. In fact, the Cass.io that I was talking about, let me show you the website. So Cass.io is designed to integrate Cassandra with LangChain, with Llama Index, with OpenAI, with all of the different It's designed to be flexible, so we can continue to add more providers, and there are paths in here where you can say, I'm using Astra or I'm using Cassandra, and it will tell you how to make it work with Cassandra. So, and then you'll be able to do all this stuff.
And there's a talk tomorrow on Cass.io.
Oh yeah, that's right. Stefano is amazing. It's tomorrow afternoon, and he's going to talk about Cass.io and how it works. This is just, what I have here is just one example of how it works, but he's going to talk about the whole infrastructure that he's created around Cassandra and AI. It's really, really amazing. So definitely go listen to Stefano tomorrow. Okay, well, I'm done. So, oh, more questions, yes.
So where is AstraDB located here?
It's a SaaS.
It's a SaaS?
Yeah.
Then you have Bedrock, which is also on AWS, so it's a SaaS as well.
Right.
Then you have Collab, obviously, which is another SaaS.
Right, you don't need Collab, right?
Yeah,
You can run the Jupyter notebooks locally.
But I'm trying to see, like in terms of the latency, I know I may have a different setup, right? But if I'm on AWS, for example, to go to AstraDB, am I going somewhere in AWS or am I going to some other cloud?
So that's a great question. Astra actually has a back end, and the back end you get to choose whether it's AWS, what region it is, GCP, or Azure. A lot of people choose to have two different regions from different providers, so that if Amazon has one of those catastrophic things that happens every now and then, you're still up and running on GCP or whatever. I don't know which part of AWS you're thinking would be moving, but
Well, I'm just thinking in terms of latency and using a lot of SaaS services, some of them provided by AWS, of course, and I know they're on AWS, but if it's provided by a third party, like Cube, right, or even some others, for
Right.
an application that is complex, you have a lot of third parties, and you want to take into consideration what's happening with the latency of my request, right?
yeah, Astra, as I've been told, and I haven't done the testing myself, but we've done testing with Astra against other databases, and we are very performant. There's not a lot of latency. Using the Bedrock, you'll probably get a little bit of latency because you're working with the two different systems, but I haven't had Bedrock slow me down noticeably.
And I think I saw you mentioned about the 5.Cassandra 5,
Yes,
which is coming out.
yes.
I guess that would be a Docker image or something like this.
You can get a Docker image now of the 5.0 beta.
I can potentially run it in my Kubernetes cluster on EKS on AWS.
Yes.
So what would be the advantage of using Astra DB SaaS?
So Cassandra is amazing and wonderful, and I love it, but it's a pain to manage. It does some amazing things with scalability, and Astra takes care of most of that for you. So you're not spending your time managing Cassandra. So the other thing that we've just added that might be interesting to people who are not excited about using CQL is we have a new, we're calling it the JSON API, and it is very similar to Mongo's interface. So if you're comfortable with Mongoose, for instance, you can drop this in and use us as the backend instead. And it's much more friendly for people who live in front-end JavaScript land to hit a document database is a very common use case.
And also here, you don't demonstrate it too much in this notebook.
Right.
But what are the benefits of AstraDB versus other vector databases, right? I think you talked about this briefly at the beginning.
Yeah, so we did some basically, Astra is a Cassandra database, and it has all the things that the Cassandra database brings with it, which is performance and reliability and uptime and you know, fast queries. And then we have vector search on top of that. It's part of that. It's not like an extra thing that we stuck on. There's a lot of companies that are just a vector database, and they're not really in a position to scale in the same way for a production system. And we did a lot of testing. I think if you go by our booth, we have the numbers, but we were like 18 times faster in some cases and 4 times faster in other cases. And we have really got the performance that you want if you're going to have a vector database.
So it seems to be an operational play, and I guess replication also, Cassandra is much better than maybe the alternative.
Yes.
That's what you're telling me, okay.
Yeah. Yes.
So if I have the regular production data that exists in the normal form, can it coexist with the vector
Yes.
within the
Yeah, you can make vector tables and they can coexist with non-vector tables.
and does in any form Astra kind of sticks these data to the
You can. The Astra wouldn't, yes.
What was the question?
Oh, the question was, if I have production data in Astra and then I want to add vector search, can those coexist? And so what I said was you can have tables that have vectors and tables that don't have vectors, but Astra's not going to bring them together for you. You're going to need to do that on the client side.
No,
Yes?
you can actually just alter a table in Cassandra and add a vector type.
Nice.
A column that's a vector type, and you
Awesome.
have to add
Awesome.
the embeddings, you have to add the data to that.
Right.
To that column, but that's all it takes to change from one to the other.
Is there a timeline between that alter and maybe
There's really no timeline for the alter. You of course have to, like I just said, you'd have to get the embeddings inserted, and that is going to take whatever time it takes to insert embeddings, just like any other data you might insert into a file. But remember, Cassandra's pretty fast at that, right? You can have multiple databases on Astra.
And in your database, you can have multiple tables, right? And so if you have a table that doesn't need vector, then you don't need to add vector. But like she said, if you want to add vector search to a particular table, then we can do that. Yes?
Is there a slide in your deck that has flow topology diagrams so you could follow it visually?
There was one. This one?
Yeah, that's okay.
And I will put my slides up. I didn't make the deadline, I'm very sorry, but I'll put them up. So if you check later today, you should be able to get my slides, yes.
So have you tested the accuracy? Do we get consistently the same result, or is there a specific domain that is?
RAG is really kind of tricky. You aren't going to get the same answer from the same model every time, even if you give it the same data. That's just the way the LLMs kind of work. I mean, I asked it the same question 5 times, and it gave me 5 similar but different answers. So that LLM piece at the completion level is gonna matter a lot. How you set up your prompt, right? That's going to be different based on the model that you have, and also you can set things such as temperature, where you tell it to be bounded in what it returns.
There's a parameter for randomness in the.
So I have to wrap up. It's 11, time for the next talk. But please feel free to contact me and ask if you have questions, or if you play with the notebook and see how it works, that would be great. And I really appreciate all of you coming, so thanks so much.
All right. Thank you, everybody, for coming to my session. Let's get started. I'm Dinesh Joshi. I'm a Cassandra committer and PMC member. I'm also an engineering manager at Apple. And today I'm here to talk to you about Cassandra Analytics. Apache Cassandra is a very popular open source database, and it's used to store a bunch of data, petabytes of data, for various applications. It's super scalable and it is very versatile, so that's why it's very popular. Now, today I'll be talking about two open source projects that my team has contributed to the open source community. They are part of the official Cassandra project. These two projects together represent a paradigm shift in how you analyze data. Either you bulk load the data or bulk read the data from Cassandra. So let's get started. Today we have a packed agenda. I'll give a quick introduction to Cassandra. Just by a show of hands, really quickly, how many of you have already used Cassandra here? Okay, most of you are familiar with Cassandra. That's great. I'll set up a problem statement on what doesn't work in Cassandra right now. And then in order to understand this problem statement, we need to talk about how we move data around in Cassandra and what is the proposed solution that we have implemented, which is covered in the Cassandra Analytics architecture. And then we'll also talk a little bit about how do you get started and some quick references on further reading if you're interested. So what is Apache Cassandra, right? It's an open source, distributed, NoSQL, wide column, highly available, linearly scalable database. If you read about Cassandra, these words, they appear at some point in its documentation. It's really great. It's linearly scalable, and that's its power. It's about 13 years old now. So it's kind of getting to a point where it is maturing as a database. Database technologies don't move very quickly. It's used to store petabytes of data, and this scale brings unique challenges to the table. So let's set up the problem statement. Like, what is it that we are trying to do, and what's the problem, right? So if you have used Cassandra in production, and you also have analytical workloads, the architecture that is proposed, has been proposed throughout the ages, is connect your live workloads like your OLTP applications that are user-facing to a data center, that is the live data center. And if you are performing any sort of analytical workloads, make sure that you use a separate data center. And most of the times we use something like Spark to process data. This is done to create an isolation between the live workloads and your OLAP workloads, right? What happens when you throw 100 or 1,000 Spark workers at a Cassandra cluster is that they dominate all of the IOPS, and your live traffic suffers, right? Your SLO suffers. And this is the reason why this is the architecture that is proposed in many cases, like just isolate your analytical workloads. These two data centers are set up within Cassandra, so Cassandra will replicate data to those two data centers. But this is suboptimal, We want to talk about how can we get to this architecture where you can actually do your OLTP workloads and OLAP workloads on the same cluster and at scale without impacting your SLOs, right? So the problem number one that we are talking about here is how do we analyze data in place, right, without really creating another data center. Problem number two that we are talking about here is bulk loading a lot of data in the Cassandra cluster. So whether it is moving data out or moving data into the Cassandra cluster while not bringing it down or impacting your SLOs, right? That is the most important thing. So when you try to analyze a ton of data in any database, this is a common problem. So this begs the question, so why is reading or writing a lot of data a problem in Cassandra? Now, Cassandra is supposed to be super scalable. You can store petabytes of data, and that is all true, right? It's horizontally scalable. But when you try to analyze a lot of data, you have to isolate that workload from your Cassandra cluster. So I'm going to give you the TLDR version, not bore you with it. We need to look at the read path of the database. The read path of the database performs a lot of work, right? So we do a network read. We have to read data out of the network buffer, deserialize the query, parse the query, look up data in caches, look up the data in memtable, check the Bloom filters, look up the compression chunks to decompress the data, and then we collect all of the results and then serialize those results and then send it back to the client. And that is a very, very expensive operation when you try to read all of the rows that exist in Cassandra, right? So if you're trying to read 500 terabytes of data, doing this operation over and over and over is very expensive, and the cost adds up. And let's not forget the coordinator. Coordinator node is yet another hop that your query goes into, and that coordinator has to then contact other nodes in the cluster, and it has to federate the response back to the client. And when you do this for a lot of rows, it is slow. It's a very expensive operation. And this is why, when you throw a bunch of Spark workers, it can cost up to 80% of your CPU just in serialization, deserialization, and all of these costs, and your live traffic suffers. What about write path? Write is supposed to be super efficient as well, and it is for the most part, right? In this case, also we do a bunch of operations, which is we do a network read. Query comes in to write data into Cassandra. We do a network read. We deserialize that query. We parse it and write to the mem table, write to the commit log, not in that order, and then serialize the response and then write to the network that you have succeeded, right? And then the coordinator node needs to make sure that the consistency level is met before it says, hey, we are good to, we have successfully written this data. There's a lot of, when you're trying to bulk load, let's say 500 terabytes of data, doing this over and over and over for each row is very expensive, and the cost adds up. So basically, writing a lot of rows all at once dominates the CPU, network, IOPS, and I/O on the disk as well. And this also creates a unique problem, like compaction. How many of you have had issues with compaction and in Cassandra? Okay, at least 40% of the room has had. So for the rest of the 60%, basically what happens is when you write a lot of data in very quick succession to Cassandra, Cassandra creates these SS tables on disk, and that causes, that impacts your read path, because now you have more SS tables to read. But also in the background, what happens is we kick off compaction, and compaction dominates your I/O on disk as well. And this basically causes Cassandra to, for a period of time, to saturate I/O on disk unless you throttle it. So you have to be very careful about creating too many compactions or running too many compactions simultaneously. Compactions should also not fall behind. So all of that is to say that if we have a way to optimally create these SS tables that leads to minimal number of compactions, you will reduce your impact on SLOs. So just to visually represent what I'm talking about here, right? If, let's say, you're using the Java driver or the Cassandra Spark connector that is out there currently, both of them basically go through the same flow. Here we have a Cassandra node that has basically some components called out here. So this is the same pipeline where we are reading, writing data, we are deserializing or serializing the data, we are processing the data, and then there are in-memory data structures that we're maintaining, also on-disk data structures like commit log, SS tables, and so on and so forth. And that's the mental model that I want to start with, right? So how did we solve this problem using or in the open source community with the Cassandra Analytics project? So going back to this diagram, basically the main cost comes from the serialization, deserialization of individual rows. Also comes from touching a lot of internal components, right? In-memory components and data structures. So what we've done in the open source community, we have introduced two sub-projects. One is the Cassandra Sidecar, and the other is the Cassandra Analytics Library. This is part of the open source Apache Cassandra project now. What does these individual sub-projects bring to the table? So the Cassandra sidecar basically brings APIs like streaming, token metadata, and snapshot. And the Cassandra sidecar essentially allows you to skip talking to Cassandra altogether, right? It has APIs to stream SS tables out of Cassandra, the Cassandra node, and into the Cassandra node, really without involving Cassandra in any part of the streaming in and out. It gives you token metadata to discover the topology of the cluster and to understand how the tokens are laid out. And then it also allows you to snapshot data. And on the other hand, we have the Cassandra Analytics Library. This is an artifact that you can deploy on Spark. And what it gives you is the ability to read and write SS tables on the Spark nodes without involving Cassandra altogether. So the part of the code that Cassandra has that takes data from an SS table, deserializes into Java objects, has been moved into this library, right? Not physically moved, but it allows you to, it exposes the API to allow you to do such things. What this means is that if you have an SS table on disk, you can point the analytics library and it can deserialize that and give you the actual rows and columns in that SS table. So how do we put these together and really improve our performance? This is basically how we do it. So you deploy the Cassandra sidecar alongside Cassandra on the Cassandra node. This sidecar runs alongside Cassandra and exposes these APIs. On Cassandra Analytics Library is basically integrated with your Spark job. And when you want to read or write data, instead of talking to Cassandra, you would talk to the sidecar. While the Cassandra Spark connector, which is the existing open source connector that is out there, what it does is it internally still uses the Java driver. So it is still going through the same path, that read-write path that a Java driver would go through. Whereas with Cassandra Analytics, you are completely skipping that altogether, right? And as a consequence, if you benchmark this, you'll find out that it is about 30 times faster to do this because you don't have to actually involve the CPU or the garbage collector or anything on the Cassandra node because you're basically streaming out data and streaming in the data without at a file level. You're not really doing it at row level anymore. So let's look at in detail on how this works and how to get started with it. Basically, when you're doing a bulk read, and this is available in the CEP 28 in the open source community, it is the whole write-up is available in the CEP. This is a screenshot I took directly from the CEP. Basically, what happens is when you start a Spark job and you are, let's say, you want to bulk read data out of Cassandra, what you do is first, the Cassandra Analytics Library has a Spark data source for Cassandra. And all it does is it goes to the sidecar of the cluster, and then it reads the topology of the cluster. It figures out what the topology looks like. And then Spark basically forks a bunch of tasks, and these tasks are the ones that go and read individual ranges of data from the Cassandra cluster. And the way they read it is they, again, go to the sidecar and stream the actual SS table files. Instead of reading each row at a time, it just streams out the entire file from the cluster. And streaming files is super efficient because we use send file under the hood, and that doesn't really impact the CPU or mainly the CPU. It does use I/O, it does use network bandwidth, but it basically goes and streams the actual file. And as a consequence, what happens is the files are transferred to the individual Spark tasks for the range of data that you're going to read. And then using the analytics library, the data is read from the local disk of the Spark nodes. And this is how the bulk read works. On the bulk write side, what happens is we materialize the data frame. So if you're familiar with Spark, Spark has a concept of data frames. And when you are writing, let's say, 100 terabytes of data in 1,000 Spark executors, each of those tasks is taking the data, that subset of data that it owns, and it materializes the data on disk as SS tables. Those local disks on Spark basically act as a staging area where we write all the SS tables. And once the SS tables are written to the original Spark task, those tasks, they again stream the data into Cassandra using the sidecar. So we do achieve some level of isolation between the Cassandra daemon process and then the sidecar. Now, once the sidecar receives these SS tables, what the sidecar does is it just calls import on the Cassandra daemon using JMX. If you're familiar with node tool import, it basically allows you to take a bunch of SS tables that exist on disk and load them into the Cassandra's working view of SS tables. And again, like when we move these SS tables into the staging directory on the Cassandra node, this operation is very efficient as well, because we are not really involving the CPU and we are just copying files again via send file semantics. As a consequence, all Cassandra has to do is just import these SS tables and make it part of the reading working set, and the SS tables become part of the Cassandra's data directory. So this allows us to skip the entire read and write path while providing isolation using a separate process on the Cassandra sidecar. So how do you get started? These projects are available on GitHub under the Apache projects, Cassandra Analytics. We have been contributing to this, and it's still under a lot of heavy development. The other project is called the Cassandra Sidecar. The Cassandra Sidecar will deploy alongside Cassandra in your Cassandra node. And then when you want to do any sort of bulk reads or bulk writes, all you have to do is just, if you're familiar with Spark, I hope folks here are familiar with Spark. How many are familiar with Spark here? Okay, I think 50% of the room. So basically, Spark has the concept of data frames, which is like a table. And when you want to do a bulk write, you have a data frame that you have obtained from a different source, and you want to write that to Cassandra. All you do is get that data frame, instantiate it, and then you call dataframe.write, and then use the org Apache Cassandra Spark bulk writer Cassandra bulk source. And that bulk source is basically has all of the magic baked in. There is a bunch of configuration that you need to provide it, like what the sidecar instances are, etc. But once you do that, all you do is like just call save, and it will do everything under the hood for you without having to touch the Cassandra database at all. Similarly, on the read side of things, you do the opposite, right? You are obtaining a data frame or a data set from Cassandra, and this basically is similar in nature. So if you're writing like a bulk job that it does data ingestion, like an ETL job, or you're performing any sort of analytical computation, right, on the data set that exists in Cassandra, you can take all of the data out of Cassandra. And the way this works is under the hood, it's going to create a snapshot on the Cassandra ring. And so you can read the same snapshot over and over without really creating new snapshots. If you want a fresh snapshot, you can always set the option to create a snapshot, and it will create a fresh snapshot whenever you run the job. But what this allows you to do is it allows you to essentially just stream all of the SS tables out of Cassandra and into Spark, and then you can deserialize them using the analytics library. So if you have existing Spark jobs, moving to this is fairly straightforward. One of the key differentiators here is that this makes your network the maximum bottleneck instead of any other component in your system. So you want to be a little careful. And on the sidecar, we have throttling controls so that you can throttle the data that is being streamed out of Cassandra. For further reading, I would encourage you to visit the wiki. CEP28 has a lot of interesting details. The sidecar project and the analytics project have getting started and readmes. It has an example where you can play around with it locally on your machine. You can set up a 3-node Cassandra cluster on your machine and then run Cassandra analytics in a Spark job and see how it feels. If you want to engage with us, you can engage with us on ASF Slack. We are part of the ASF Slack, and if you want to engage with us, you can also engage with us on Jira or the dev list on cassandra.apache.org. That's pretty much it. Thank you. I'm not sure if I have time for questions, but yeah, if anybody has questions, I'll be happy to answer them.
Any specific versions?
So the question was what specific version of Cassandra this works with. So we currently support Cassandra 4 and by extension 4.1 as well. There are plans to support 5.0 of Cassandra. So if you are on Cassandra 3, it's a bit tricky. But the idea is to support version 4 and later going forward. Yes? Yes, I was the author of the zero-copy streaming work in Cassandra. So yeah, so this is similar work, an extension to that work. Yes?
For the bulk feed use case, I'm assuming you cannot specify filters.
Yes.
Because you are restreaming the whole SS file. So any filtering that has to be done after the fact. Am I right?
Yes. So the question is like, where does this filtering would sit, right? So in this case, since we do not have visibility on what we are not inspecting the actual SS table files, we don't really look at the partitions in the SS table files or the tokens. The data is actually streamed as a whole file. So if you want to do any sort of filtering, you want to do it on Spark. So this is an important observation. This is useful for workloads that actually need to pull out all of the data or pretty much all of the data. So if you have a highly selective query that you want to run against the cluster, this is not the tool for it. Yes?
What's the consistency guarantee for this mechanism?
That's a Yeah, so that's a great question. What's the consistency guarantee? So the library understands the token metadata and the cluster configuration. So it looks at the key space and it ensures that the data that is streamed meets the consistency guarantees of your tables and key spaces. And you can't, I don't believe you can specify a consistency level, but if you have a consistency level in your key space, that consistency level is met. So we do actually do an in-memory compaction and remove all the tombstones and everything. And we are streaming data from the two replicas and ensure that the two replicas are in agreement indeed. If not, then we pull data from the third replica and ensure that your consistency level is met. Yes?
Can you tell me again what the sidecar does? It just reads and writes to the SS table?
So yeah, for that, I would say look at CEP1. The Cassandra sidecar is meant to be a management process that sits, it's a co-process that sits alongside Cassandra. It exposes a bunch of REST services that allow you to manage Cassandra. As of now, the concrete use case that we have is the analytics library that allows you to stream data in and out of the Cassandra node without actually involving Cassandra in the read and write path.
But it takes a sidecar instance, so you need sidecar to run that.
Yes, so from an operational standpoint, you need to deploy sidecar alongside Cassandra for this to work. Yes. Sorry. Yeah, go ahead.
A couple of quick questions. So, one, what is the sort of separation between processes from a security point of view? Is there any, like sidecar and especially Cassandra running? And two, you said this is something that has to be installed on the node separately, right? Or is it part of a Cassandra distribution?
So the two questions is the separation in terms of security model, and the other question is is it part of Cassandra? Yes, so we have not yet cut a release, 1.0 release of the sidecar or the analytics library since it's under heavy development in the open source. So basically, it's not part of a Cassandra distribution. If it were to be released, it would be released as a separate artifact alongside Cassandra, since it's not really tied very deeply with Cassandra. In terms of the security story, authentication would be via mutual TLS. That's something that is work in progress and we would be open sourcing at some point. There was a question in the back.
These libraries, the libraries sidecar and
So it is currently available in the open source repository as code. You can build it yourself. We've not yet had a release of it. As soon as we have a bunch of features worked out, but you can actually build it yourself and run it. So I don't have, unfortunately, a concrete date for you on the release, but the team, we are working on it. I believe Spark 3, 2 and 3 both. And I think there's a whole matrix on the documentation on the version of Scala as well. So Spark and Scala are together. And then there's JDK Java versions as well. So there's a bunch of matrices. I think, okay, any other questions? We have 3 minutes. Yes. In terms of disk IOs, since you're streaming the entire files out, there would not be any technical reduction in disk IOs. I get what your point is. We will see probably IOPS reducing, but not the actual IO to the disk. So you would still have to stream the same amount of data that sits on disk over the network. Yes. So yes. So in terms of the infra cost, if you're talking about the number of nodes that you have to run, since Cassandra Sidecar is a pretty lightweight process, it's a Vertex NetE application, you don't really have to allocate too much memory. So there will be some delta increase in the cost, but not like 2x or 3x of cost. Cool. There was one more question in the back. So I think so the question is, what is the resource allocation? So you can always run the sidecar with like a 2 gig heap. It doesn't require a whole lot of heap space since it's not doing anything for the most part, right? And in terms of CPUs also, a couple cores is more than sufficient for the process. It's a fairly lightweight process. There was one more question here. Yes?
Thanks for sharing. I have questions on like the read bug, all read bug. So what from our side, what we do, we use Cassandra, we take snapshot and send it to S3. From there, we have a high band and whatever field. So how that like is different from the stuff. I'm aware of the CPU. Just want to your perspective, like since we are using AWS.
Right. So the question is about the what's the difference between sending these SS tables, snapshotting them, and sending it to S3, and then connecting to the rest of your infrastructure versus this. So it's perfectly fine to have that pipeline, but with this approach, you don't have to incur the S3 cost at all. So if you have Spark and you're already processing data on Spark, you can directly read data from the Cassandra cluster. Now, if you happen to have Spark deployed in the same VPC, same zone um, as Cassandra, then you are really not incurring any bandwidth costs either, right? So you can actually create the snapshot and stream the snapshot to your Spark directly without actually involving S3. That is the advantage here. So the only additional cost to you is to set up the sidecar. And I'm assuming that for pretty much anybody who runs Cassandra also has their internal tooling, which has some form of an agent or a sidecar that runs alongside it. And the goal for this project, the Cassandra sidecar project that we proposed like several years ago, was to ensure that there is a community-supported sidecar version. All right, I think we are out of time. But if you have questions, I'll be happy to talk to you in the hallway. Okay.
Hi, my name is Yuki. I'm a principal architect from DataStax and a long-time Apache Cassandra committer. Today, I'd like to show my work that I've been working on for quite a while, which is a OpenTelemetry integration into Apache Cassandra. So how many of you know about the OpenTelemetry project? And do you already deploy OpenTelemetry to your environment? No? OK. Yes. Thank you. So yeah, this is the talk about using OpenTelemetry to send all the telemetry from Apache Cassandra. And I like to show my demo in this session, so you can maybe in the future, if you deploy Apache Cassandra with OpenTelemetry, you can get much more insight in one place. So OpenTelemetry, this is a open source project hosted on CNCF. And historically, it is a merging project between the Open Tracing project and Open Sensors project. It provides a observability framework, so you can use OpenTelemetry to instrument your application. It is a language agnostic, so if your application is whether it's written in Java, Python, or Go, you can use OpenTelemetry to instrument your application. And it also provides a specification to send those telemetries out to any APMs that supports OpenTelemetry. So this is taken from their website, and yeah, it's basically just what I said. And the other important thing for this project is it's vendor agnostic. So whether you use open source Prometheus, Jaeger for tracing, or if you prefer to use commercial offerings like Datadog and Splunk, they also support OpenTelemetry. So you can choose between those products to use to monitor your application. So here's why I decided to work on this my own personal project. So as a consultant at DataStax, part of my job is to troubleshoot various problems in customers' cluster, right? And to do so, I need the information from the customer's cluster. So I ask a DBA what queries the application is running, or can you show me the metrics, or can you get me the logs? And oftentimes, yes, they set up the monitoring system to get all the metrics from the Cassandra cluster. But when I ask about the application query, the people I interact with are mostly the DBAs, and they don't know the answer. So they need to ask the app team for the schema and queries and read and write patterns, and that takes time to get me information. And the logs. If the project is rich in budget, they have a log collector system set up in their application. So they can go into the central place to look for the log. But most of the time, they don't have those luxury stuff. So people need to log into each node in the Cassandra cluster and get me the log. So before I start analyzing things, there's a huge gap or wait time to collect those information. And when those are in my hand, I just start piecing all those together to do the troubleshooting. Right? So yeah, those application logs, the query logs, the metrics, and actual Cassandra node logs, those are the key to the system's observability. So if you look up the observability and search for the web, you can see these keywords, 3 pillars of observability, and which are the tracing, metrics, and logs. And these are the things actually already Cassandra has in a long time. For the tracing, we have a tracing on capability since Cassandra 1.2. And if you turn on the tracing and run your SQL query, it logs all the internal stuff into the Cassandra table, so you can take a look at what's going on when you run the SQL query. All the metrics, Cassandra is instrumented with a metrics library, and it has a huge amount of metrics that you can extract it from. And because the Cassandra is Java application, those are by default are exposed to Java's the formal JMX method to get the data. And the logs, Cassandra has a logback library built into it, and by default, it emits the unstructured log to the file. But getting all those data out from the Cassandra cluster is, as I described, is very hard for the people sometimes. And tracing, there's no way to export in the current state. So it is in the Cassandra table, so you can just dump those stuff into CSV, but still, you need to, collidate with other stuff by hand. Metrics, yes, it is exposed to JMX, but you need to somehow install JMX exporters to get the data out. And the logs, yeah, you need the file tailing stuff to extract the logs as well. And it is unstructured, so sometimes if you get the exception or the error, you need the weird stuff to actually preserve the stack trace from the log. So here comes the OpenTelemetry. As I mentioned earlier, OpenTelemetry defines the way to export these 3 pillars of telemetry through the standardized protocol. So integrating OpenTelemetry into Cassandra will make our life easier to extract those observability telemetries into the external system. So yes, if you have OpenTelemetry capability, you can export these 3 pillars of observability to any APMs that you are using currently. So I'd like to show the demo that I built, or I've been building for a year now. And so this is a small diagram, but you can see this in my GitHub repository that I can show you later. But I set up the Kubernetes cluster on Amazon. I deployed a 3-node Cassandra cluster that I also instrumented with OpenTelemetry. And I deployed the web application, which is built using the Spring Boot framework. And all those application and Cassandra node are deployed with a OpenTelemetry collector as a sidecar. So each application servers or each Cassandra node can send telemetries to that collector. And there's also a centralized OpenTelemetry collector cluster that forwards those telemetries to outside system. And for this demo, I set up this centralized OpenTelemetry collector to send the gathered telemetry to Datadog, Honeycomb, and AWS CloudWatch. So I'd like to demo my application here. So this is a Spring Boot application, and it talks to the Cassandra and reads these products information from the Cassandra cluster. So if I click on the T-shirts category, it shows all the T-shirts, and if I click on the products, then it shows the product. And these data are fetched from the Cassandra. And every time I access these URLs, it generates the telemetry, both from application as well as a Cassandra node. And this is the Datadog dashboard that I set up. And it is getting the data from the OpenTelemetry collector in real time. And if I, for example, access a product, so maybe so this is a trace from the application, to get the product pricing. And if I go into this, as you can see the tracing from your application as well as what's happening in Apache Cassandra. And you can see the query that this application is executing, as well as what's happening on each node when the Cassandra is doing when executing this query in distributed way. Right now, it is emitting the same information as a Apache Cassandra tracing. So things like a read request message received, those are the exact same events that you can see in the Apache Cassandra tracing. If you go into the metrics, you can get the various Cassandra metrics in the same Datadog application. So you can like show the compaction, by it's compacted, and you can create a dashboard from these metrics. And I also send the log file from the Cassandra. So these are all the log file that's emitted from every node in the Cassandra. So using this OpenTelemetry instrumentation, you can send the 3 key telemetries to one central place. The same telemetries are actually sent to other APMs like Honeycomb, and you can see the tracing in Honeycomb as well. So these are the other URL access, and as you can see, it shows the application tracing as well as the Cassandra tracing in one place. The same thing for CloudWatch. You can get the tracing from Amazon X-Ray, just like I showed in the other APM applications. So as you can see, integrating OpenTelemetry into Cassandra has many potential for operators of Cassandra to troubleshoot the internal of Cassandra in one place. And OpenTelemetry also has a capability to correlate each of these telemetries together. So if I put more effort into this demo and put more implementation to this, I can probably actually correlate tracing metrics and logs in more meaningful way. So the highlights of the demo is application like Cassandra send telemetries via standardized OpenTelemetry protocol, and the collector will export it to various APMs, so you can monitor these telemetries in one place. The code for this demo is available under my GitHub, Cassandra 5.0 modification with OpenTelemetry, and the application side as well. And the last one also has the same diagram that I show in this session. So let's take a look at the implementation side. The goal of this implementation is actually enable operators to easily turn on this feature and sending the key telemetries to outside world. So I'd like to add only one Cassandra YAML configuration, OpenTelemetry enabled, and if the operator turns on this, the Cassandra can immediately send telemetry outside to the cluster. But of course, there's a couple of things you want to configure. So I use this OpenTelemetry SDK auth configure extension so that when necessary, the operators can customize their OpenTelemetry properties as they deploy the Cassandra. So in my demo, I used a environmental variables to specify, for example, OpenTelemetry service name or some sampler configuration like this. But you can also use a Java properties to configure things. So you can put the same information in jvm.options file to configure these behaviors. And to enable a OpenTelemetry tracing, I need to change a couple of things. So the first thing is taking the same tracing context from the application. So for that, application needs to send the tracing context information to Cassandra, and Cassandra also need to propagate the tracing context information to other node. And there's a couple of places that I need to be modified. And one is a native protocol level. But fortunately, current native protocol supports adding custom header to its messaging. So I can just use a standardized tracing context format there to get the context from the application and propagate it to Cassandra node. And for the messaging between the Cassandra nodes, we already have a Cassandra tracing capability, so which does the similar tracing propagation between the nodes. So all I needed to do was to add the new message type, trace context, and just serialize what the necessary attributes into the messaging header, just like a current Apache Cassandra tracing does. So to put these tracing context in the same tracing ID. And for the metrics, I don't think changing everything and instrument using only the OpenTelemetry takes very long time, and it needs to make a huge change to the current code base. So what I did here is to listen to the metric registry, and as the new metric is registered through this current metrics library, I can just put the listener to listen to the metrics, and the OpenTelemetry SDK, you can just poll the current metrics and expose it to OpenTelemetry protocol. So I use that to not change the current code base, but only add one more layer to extract the metrics. And for the logs, the Cassandra uses logback library to write the logs to file. And OpenTelemetry Java project has this logback adapter to actually change the logback log event into the OpenTelemetry log event object and send it to the OpenTelemetry protocol. So I added one line into the logback XML to use this OpenTelemetry logback adapter, and that's all. And it just starts sending the log to outside world. So all of these changes that I mentioned in today's session, I'm drafting the official CEP, CEP32, to make it the default Cassandra feature in the future release of Cassandra. It is still in the draft state. I started writing like a year ago, when the OpenTelemetry standards are still evolving. So I need to update to the current state of OpenTelemetry, and I need to update my code base to apply to Cassandra trunk branch. But all the information that I give today are more described in this CP that I'm working on. So that's my session today. And I'd like to hear more from you about this CP. And you can reach me with this YUKIM handle on Apache Slack or GitHub or Twitter. Or you can just email me to the Apache mail. So no, we can discuss more on the topic to make this official Cassandra feature. So thank you very much for listening. And if you have any questions, I can answer. Yes.
To collect the tracing data, you have to have tracing enabled. Would that cause any kind of latency increase for the reads?
Okay, the question is about the latency impact when you enable the tracing. And I say yes, but I didn't do any performance impact analysis. But as I show here, you can actually tweak your sampling rate, for example, to get the tracing on how frequently you want to generate these metrics. So maybe you can tweak that to make the performance impact minimal.
Does this work on 4.x version?
Okay, the question is, does this work on 4.x? When I started this work, it was for 4.0. So I have a 4.0 version of demo from last year, but I updated this to use 5.0 for this year's presentation. But I don't have any 4.1 implementation for this. But it can be easily adapted. I think the porting from 4.0 to 5.0 was very, very minimal change. So. Right, if there's no questions, thank you very much for coming to my talk. And I hope to, see you soon.
Testing, testing, yeah. Let me talk to you. Testing, testes. 1, 2, 3. Nice. All right. Let me talk to you. All right, that's fine. Sounds good, sounds good. Just want to make sure we work. Testing lab mic 1, lab mic 1, testing. Lab mic 2, testing lab mic 2. Well, it's got no sound to it at all. How is this EQ? It's not EQ'd, that's why. Testing, testing, testing. There we go. Mic, lab mic 1. Excuse me, 2, lab mic 2. All right.
Hello?
Hello. Hello.
Hello?
Hello. Oh. Hello. Can we test with the mics on? Hello everyone.
Hi.
Hello everyone. Yeah, that sounds good. Today we are here to talk.
You gotta remember the speakers aren't pointed at you guys, so it's louder to us than it's gonna be to you a little bit.
Oh, okay.
But she is still kind of soft.
Hello everyone. Thank you. Hello everyone. Today we are here to talk about Apache Cassandra Sidecar. Cassandra Sidecar is a management process for managing Cassandra database. Briefly about us, I am Saranya Krishnakumar. I have been working at Apple as a software engineer, and for the last 4 years I have worked on various projects related to Cassandra Sidecar.
Yeah, and my name is Francisco Guerrero. I'm also been working with Saranya for the past 2 years in the Cassandra Sidecar project.
Today we will go over what is Cassandra Sidecar and why we need a sidecar process for Cassandra database, what is its architecture, some of Sidecar's use cases, and how developers and users can get started with the project. Finally, we will conclude our talk with a summary. What is Cassandra Sidecar? Cassandra Sidecar is a control plane that has been introduced for managing the Cassandra database. It is a separate JVM process that runs alongside the cluster. To run Cassandra out of the box with zero configuration, we need a control plane that provides essential functionality. Hence, authors of CEP1 proposed adding a sidecar into the Cassandra ecosystem. And with the control plane introduction, operators can now directly interact with and administer the database through HTTP APIs. They did not learn any new tool or programming languages for operating the database. Sidecar also passes the curl test. We had scale in mind while building Sidecar. It can handle queries at scale, and the architecture of Sidecar is pluggable and extensible. It can be adapted to run and support Cassandra clusters of various Cassandra versions. We will go over the architecture in detail in coming slides. Why do we need a sidecar process? Cassandra clusters are generally hard to operate. We need various automation tools for maintaining the cluster. For example, we need maintenance tools for restarting clusters, and we need migration tools for moving data from one cluster to another. And apart from operating, we also need execution tools for executing commands at bulk in Cassandra. Hence, we need a sidecar process that combines all of these maintenance, operations, and execution into one process, and the sidecar can provide these functionalities through REST APIs. And with REST APIs, the interactions will be easy and both straightforward. Some of the functionality that has already been added to sidecar are running health checks and getting a view of the cluster, getting cluster settings, capturing data, capturing a snapshot of the data, and streaming data to and from Cassandra. So a control plane solution, for example, in a control plane solution will have all these functionalities in one place, and it will be a common control plane that is introduced in open source. In a previous talk by Dinesh Joshi on Cassandra Analytics, he went over how read-write path of Cassandra is very expensive and how it has various steps included. Cassandra Sidecar will also allow us to bridge gaps when directly talking to Cassandra is expensive. Sidecar can directly access the data directories of Cassandra, and hence bulk reads and writes can be easier with Sidecar. So why the effort in open source? The main motivation behind building a sidecar solution in open source is that because of the complexity of operating Cassandra, everybody will have their own sidecar solution in their environment. And this effort was more to consolidate all that and have a control plane in open source. Now I will hand it over to my teammate to talk about the architecture in detail.
Yeah, thank you, Saranya. Yeah, let's go over the architecture, and we're going to deep dive into some of the details of Sidecar. So Sidecar is built on top of Vertex. Vertex itself is a toolkit to build reactive applications, and we wanted to leverage this asynchronous nature of and reactive of Vertex, because this allows us to scale up as the workloads grow. It also offers resiliency when we encounter failures. As it stands today, Sidecar is a stateless process. Vertex itself is built on top of Netty. And in a traditional application server, we have something like this. We get a request, and a single thread is going to be handling the request during the life cycle of the request. That means that if we do like some database access, or if we go to the file system, or we talk to S3 or we have some blocking I/O operation that is very expensive. That thread is going to be wasting CPU time. So we can see that in this slide how we have multiple threads, and in the red we have these blocking I/O operations. So these traditional application servers are well suited for like medium workloads, and as your workloads grow, you need to scale horizontally. You need to add more resources, more boxes to be able to handle more requests. So for that reason, we decided to use the asynchronous programming model that we get from Vertex. And that allows us to reuse resources more effectively. We don't need that many threads to process requests. When we have a blocking I/O operation, we just move on to the next task, and then we can come back to the initial task when that blocking operation completes. So Vertex multiplexes concurrent workloads using the event loop. And that allows us to use the hardware more effectively. We can handle more requests. And that's what we need for a project like Cassandra, because we're dealing with massive amount of data. Let's take a look at the components in Sidecar. So we have a server, we have a Java-based client, and we recently introduced the InJVM distributed testing. In the server, we have route handlers, and those are gonna, when we get a REST request, we're gonna be routing those requests to the specific handler. We have adapters for different Cassandra versions, and we have periodic tasks. For example, we do periodic health checks to the database. The Java client was recently introduced as well, and it has a lot of features. It's feature-rich client that allows us to do retries. We can have retry policies and exponential backup, and we handle different status codes from the server. And the InJVM distributed testing was a massive undertaking to bring it over to the Sidecar project. And this allows us to build a more robust project, and we have more confidence of the project, and we know that the project that we are putting out there is well covered in terms of testing. So that was a big effort that we did to bring it over. Looking at the server can manage the Sidecar server can manage one or more Cassandra instances, and we perform health checks on every of the instances that we manage, and then we can adapt to the different versions of Cassandra. So we can see that on the left we have the Sidecar process, and on the right we have a Cassandra ring. So we can handle one or more instances. And we have these adapters. So let's say we want to do an SS table upload. We have a handler for that. We want to do an import of data. Or if we want to get the schema of a key space, we have all these adapters. And we have, we have all these handlers, and we have adapters, and these adapters are version specific for Cassandra. So, this means that they are tied to a specific instance of Cassandra. So if we run in a mixed mode, we would have an adapter for this instance, which is running Cassandra 4.0. And we would have different adapters based on how many instances we are managing. And the way we talk to Cassandra is via JMX and CQL. And the adapters give us the interfaces to talk to Cassandra. So we have interfaces for the storage, or for cluster operations. We have all these interfaces that are abstracted for different versions of Cassandra. So let's say we want to run like an SSTable import. We get a REST request for instance 1. This request is going to get routed to the correct handler. So we would use this import handler. And then we need to get a reference for the Cassandra adapter. And that is going to be specific for that version. So we know that we're going to be running the JMX command to do the imports. Now let's say we want to do we want to upgrade to Cassandra 5. So what Sidecar is going to do is it's going to notice that there's going to be a disconnection when we bring this node, when we start to upgrade this node. So we no longer have the adapter. And we are still going to do the health checks. And when we are able to establish the CQL connection, we can bring a new adapter. And this adapter is going to be for Cassandra 5.0. And because we have these interfaces that are transparent to the handlers, we are still going to be able to serve requests. So we established the JMX connection. And that's how adapters are created and managed per Cassandra instance based on the health checks. And then I'll hand it back to Saranya. She's going to talk about use cases.
Thanks, Francisco. Now we will go over some of the use cases of Sidecar. Sidecar enables faster analytics. Through CEP28, analytics project was introduced in open source for bulk reading and writing data to and from Cassandra. Sidecar provides some of the key functionality needed for analytics project. It provides REST APIs that can stream data directly from data directories using zero-copy streaming technique, and it does that without loading data in memory. It also has REST APIs for importing SS tables into the data directories after performing validations of data. With analytics project, bulk reads and writes are at least 30x faster. So what is the impact of analytics on Cassandra? Computation needs are now needed for bulk reading data out of Cassandra are now moved out of Cassandra into an isolated process that is Sidecar. Bulk reads through Sidecar have minimal impact on I/O during disk reads. We also have throttlers in place for both checking the bandwidth used and for checking the number of connections created to avoid overuse of CPU. During bulk writes, through the analytics project is much faster than regular writes. Analytics is only one of the use cases of Sidecar. More such use cases are coming. So getting started. Developers and users can get started with the project. The project is present under Apache here. And there is a README as part of the project, which will help getting started with the IDE, setting up the IDE. For experimenting, you can start a local 3-node cluster and run Sidecar out of the box with minimal configuration change to the YAML. There is a dev module that is part of the project which allows for this local run. And we warmly welcome new contributions. Some of the areas of interest are cluster-wide APIs and adding authentication and authorization to Sidecar process because securing the process is important. And you can also add scheduled tasks to the management process. We track open issues through Apache Jira, and interested people can join the dev mailing list where we talk about features, bugs, or in general chat with the community. There is also an ASAP Slack channel. Now let's go over the summary of our talk. In our talk today, we saw what is Cassandra Sidecar and how a Sidecar process acts as an interface between operators and the database. And it provides some of the key functionality needed for maintaining the database, and it does that through REST APIs, which is easy to interact with. We also saw in detail about Sidecar's architecture. It is a pluggable and extensible architecture that can be adapted to support various Cassandra versions. We saw some of its use cases. Thank you for taking an interest in our talk. We can move over to Q&A.
Yeah.
So do you think that sidecar can talk to other sidecars, for example, for some orchestration purposes and so on?
Not yet, but there are efforts to bring that over to Sidecar. So some coordination to be able to have some sort of leader election for different purposes. So that's
Just for example, like if you want to take a snapshot, for example, right? So you need to do it as many times as many nodes you have.
correct.
And like if you have some kind of a coordinator, let's say, that specific sidecar could tell all the other nodes, hey, take a snapshot.
Yeah, and that's part of the CP1. Like one of the things that we wanted, or Sidecar wants to address is this cluster-wide API. So you just need to talk to a single sidecar, and this sidecar is going to do the coordination. So that's part of the CEP right now, but yeah, that's something that we definitely want in Sidecar.
Also, you said there is a Java client. Is it manually written or is it generated?
Currently, it's manually written because we wanted like some customized features, but there were efforts to have it automatically generated, which I think it would be better. You wouldn't be tying to like Java. You could have clients for other technologies. So the question is the proposal for Sidecar to talk to different sidecars or to multiple Cassandra processes? Okay. No, I think the proposal is for Sidecar to be able to talk to other sidecars, so do like some coordination.
A lot of different folks at different companies have written their own sidecars to manage Cassandra, and there are a lot of divergent implementations of some of the same functionality. Are you finding anything interesting as you've reviewed some of the different sidecar implementations that are informing work that happens in the official one?
We've seen like, yeah, multiple sidecars, and everybody's doing things differently. So ideally, we want to consolidate all those efforts into a single project. And that's why we came here to talk to you, to be able yeah, we want to get people together and make them learn more about the project, and hopefully we have like a single community-driven sidecar, which everybody's going to benefit from a single project.
So is it strictly required to run sidecar in the very same physical machine, or you can just talk to the to JMX like remotely?
So Sidecar can talk to the instances it does through JMX and SQL, like we covered, but for having the advantage of it being able to make communication faster, like for example, directly streaming from data directories, we need it to be able to read the file system.
Yeah, so for these bulk operations that we introduced, yeah, we need file system access. Yeah, you can do a data frame read and then write to a different cluster. And the advantage is that if you have clusters with different topologies, Spark is going to repartition the data such that you read from the original topology, and then you repartition the data for the target topology of the new cluster. Yeah. Okay. Yeah, thank you. Thank you very much.
Yeah, so it's a little bit loud. Can you, okay. Welcome. So I think this is a potentially common theme, but obviously the slides have changed since March. Nathan Jacobs, and I'm a principal developer at OSI, and we run big clusters. So I've been with OSI for 8 years using Cassandra in our Historian product. We work on operations technology solutions, so utility, electric, gas, water, transportation networks, manufacturing, kind of anything that has a control system. That's kind of our core business, and Cassandra is an excellent time series database, and we've been using that as a part of our Historian product for the last 10 years, and I think it's been pretty successful. We've shipped for customers hundreds of clusters, centuries of data, petabytes of data, all kinds of deployments, and it works. So kind of what's the customer use case of why you would want to use Cassandra as the backing database to a historian? This kind of common knowledge for the Cassandra community and its strength in time series data. For most of our customers, it's a 90% write, 10% read kind of use case. From a regulatory perspective, electric utilities in the US have to have a kind of a black box recorder of what's happened so that if there is an incident, then they're able to go back and analyze and learn from that failure in the grid and change procedure to increase resiliency. We do have some other cases where it's the exact opposite. Some customers use the historical data on distributed green, solar and wind generation to train models to predict what kind of power generation they'll have in the next days, weeks, months, to plan the more firm, gas and coal generation to match what the renewables will be able to provide, and so effectively helping to make the grid greener. And it's highly available and resilient, right? It's you think about the CAP theorem, and Cassandra is available and partition tolerant. So in a worst case, you can still go down to local one consistency, and everything still works. And unlike the legacy RDBMS databases, it's not blocking on a lot of operations, and so everything scales out linearly with additional compute and disk resources. And that's important because the grid it's backing some of the data in the grid. Operators of the grid are relying on this data to give them context to what's happening right now, and so it has to work. It's not really something that we can say, we have to patch this, or something happened, it's not available, right? And I think most people that have worked with databases for a long time have seen some kind of issue where a database isn't available because of some issue in the backend, right? Like I've seen Mongo replicas that fall too far behind the leader, and you have to basically reinitialize them, or Postgres instances that have a subscription that disappeared on their peer, and it says, I can't start because I can't create the subscription for the replication. Cassandra doesn't have that issue. It just starts and runs and works. And then it's also very cost and hardware resource efficient. We've taken a look at some other time series focused databases, and in nearly every single case, Cassandra is 50% less disk space, or somewhere around that area less than the other databases. And because there's less locking, it's more efficient to compute, and we're able to run with fewer resources than we would need in another database. Compared to a traditional RDBMS, we can scale to orders of magnitude more data than you would ever be able to run in one of those traditional databases. And then why does the business care that we're using Cassandra? What are the benefits to us that don't necessarily impact the customer? It's incredibly fast ingest, and so we're able to run extremely dense instances. We're able to convert data from a legacy historian into our solution very quickly. I think a common thing that everyone's heard is that Cassandra runs, it can ingest data as fast as the disk can write it. Your compactions will build up, but it will accept the data that quickly. It's incredibly scalable, and so we effectively don't change any schema, GC tuning, anything. It's basically the same exact configuration, And we run that same configuration on clusters that store anywhere from months to multiple decades of data, 1 or 2 instances to dozens of instances, and all kinds of hardware deployments. I think because they're utilities and they can't, it has to work, we can't necessarily rely on an ISP and a connection to the cloud. So probably 90% of our deployments are on local, on-prem physical hardware, although we are seeing a lot more virtualization and hyperconvergence solutions being demanded. And so kind of what's the current understanding of what our limitations are? About 10 years ago, I think the typical recommended instance size was somewhere between 250 and 500 gigabytes for an instance. The current recommendation is 1 terabyte with, if you're using size-tiered compaction strategy, you need to have double the space to handle major compactions. And we're not the only ones running bigger than this. Obviously, DataStax has a lot of expertise, but this is how we approach the problem. So the kind of the limiting factors to how big an instance can be are based off of your query throughput, how risky you want to run your replacement times, and what kind of your ingest and repair frequency are. So basically, compute requirements scale linearly with query demand, and you can only get a server with so much CPU. There are 4 socket servers out there, but at some point you are going to have to scale those out horizontally. That is an upper bound. SS table count, if you have, the more SS tables you have, the more time you're going to spend looking for your data. It's going to increase your latency. Increasing your latency means that you're spending more and more time handling those queries, so you want to keep that SS table count down. But in order to keep that count down, you need to run more compactions. That also adds CPU and I/O load to the system. And then, whether you're using TTLs or deletes, you're going to have some kind of load deleting the old data because disk doesn't grow forever. Everyone has some kind of retention enforcement policy in their system. Replacement times, again, instance size is going to be a factor here because it relates to how fast you can copy data. The bigger your instances, the fewer instances you have to stream the data to your replacing instance. And if the replacement time takes too long, then you're going to introduce more load on the other servers in your cluster, and you're going to introduce, with that demand, you're also putting yourself into a case where, if a second server fails, you're introducing even more load, and it could eventually cascade to where a service becomes unavailable to the user. And repair consistency, you have to eventually have your data repaired. The more data you ingest, the more data in the instance, the longer your repairs are going to take. And eventually, you might not be able to catch up if there's a hardware failure that prevents you from running the repair, since repairs require all nodes to be up and running at the same time. So our first kind of approach to this is to promote some of the partition keys you would normally see to a key space level. There's kind of a trick that carries over from the legacy RDBMS databases where you'd create a new database each month in your SQL database, and then you would drop it at the end of the month. This is kind of like time window compaction strategy, but at a key space level. And this has a number of benefits for us in how we run our clusters are ran. So for the first thing is there's no TTLs. This means that we're very flexible in how long the data is stored in the system. A lot of customers are like, I paid for this hardware, I want to use this hardware, don't delete it until I tell you. And so if we had a TTL, we wouldn't be able to give them any flexibility on that. We can either say, you're ingesting data faster than you told us you were going to, we're going to clean it up sooner, or your data is coming in slower than you thought, or you over-provision the cluster. We're going to delay until kind of the last possible moment to drop that oldest key space. And so most clusters run around kind of 95 to 98% utilization of disk. So our disk utilization is much higher than kind of the typical 50% size-tiered compaction strategy. I think time window compaction strategy you can normally get kind of a lot closer, but because it's a TTL, you can't necessarily predict when your disk is going to fill up, so you might have to be scaling your cluster out or in to kind of drive that cost savings. The other benefit is that kind of partitioning with a key space, it's actually based on the data in the table. Time window compaction strategy, it windows the data by the right time, not by the data you're looking for. And so, for example, we have a 20-year retention period cluster. If we had that all in one table with time window compaction strategy, we're checking every single SS table, at least at the Bloom filter level, for whether or not there's data that we might need for a query, even if it's only the last week's worth of data. Versus with this, we're reducing that SS table count from 240 months worth of data down to just the most recent month's worth of 6, 8, 10 SS tables, at least while the data is still being archived. And so that dramatically reduces how many SS tables you have to consider in a query compared to time window compaction strategy. You don't necessarily get the major compaction at the end of the month like you do with time window compaction strategy, but that's as simple as setting up a cron job and run that a day or a week once that month ends, and you get a good speed up. I think we had one cluster where a customer was doing a lot of reporting. It was a physical server with hard drives for disk, and they saw a 4 times increase in throughput even with the monthly key spaces after running major compactions on each month that had finished archival. And then what about replacing instances? So our first approach is to, whenever possible, run with replication factor equal to the number of instances. And so in that case, we can basically clone, and if an instance fails, we can just blow it away, clone an existing server, and that's the replacement. So we start by taking the system key spaces, copy those over, you flip one row between system local and system peers, and you have exactly what was supposed to be there in the first place. The other nodes in the cluster haven't been told that instance died. They just see it as down. So you've effectively bootstrapped it without copying any of the client application data. And that's a lot faster than having to copy all of this data over the gossip service. And then once that system key space is created, we can snapshot one server and copy all of those snapshot data back to the server we're replacing. And because our replication factor equals node count, in most cases, we've effectively brought back all the data, and we have our repaired at timestamp in the SS tables, and we don't lose anything as far as tracking when repairs, what data needs to be considered for the repair to finish making all the data consistent in the cluster. And it also is a process we've used for manual repair. Don't use SAN, but we did have a case where a customer was using SAN, and we had to manually repair using this kind of approach because the gossip service wasn't able to keep up, and compactions were building up too quickly. But it is a way you can kind of save, you can push out the deadline on replacing hardware if you absolutely need to. So with that said, what are the reasons that we scale horizontally, which I'm not recommending everyone scales vertically like this. We have some constraints, obviously, in how we have to approach our systems to be able to get away with this. But the two main things that drive us to scale it horizontally are the repair throughput per instance and how much storage we need in the system. So for repairs, it's a compaction-based process. You generate your Merkle trees to figure out what data has to be copied. You actually stream the data, which at least as far as 3x is a compaction process that might have changed in 4. We're only evaluating 4.1.3 right now. And then after streaming the data, you run an anti-compaction to mark the data as repaired. On a server CPU, you get about 10 megabytes a second of throughput. So with having to do that 3 times, you get roughly 3 megabytes a second of throughput on a repair session per instance. We prefer to have repairs run during off-peak hours, and we prefer to have it only last about an hour so that we have plenty of time to catch up in the case of a hardware failure. So each instance can roughly ingest 300 or 350 gigabytes per month before we start to get uncomfortable with how quickly that data is coming into the system. So when we have to ingest more than that, we'll scale it horizontally. And so for that example, kind of the title slide, the 80 terabytes per server, That's running with 5 16 terabyte instances as a result of that ingestion rate. The other case is when we have a very long retention period where just RAID arrays get too big for us to be comfortable with the rebuild time or how likely it is that we're going to have to rebuild the data. And so in that case, we scale out horizontally because then we have the data spread out across smaller RAID arrays on those hardware servers. And a cost optimization that we're able to do when we do scale out horizontally is use very dense servers. And so one of the clusters that we've deployed uses the server in the lower left here, a Dell 740 XT2, which has both of these servers. The other one's a HP Apollo 4200 Gen 10, I think, and both of these have dual backplanes. So with Cassandra, it's all about compute, it's all about storage, and you can get extremely dense configurations with this. I think the 80 terabyte example is only using one backplane, so we could theoretically go to 160 with 10 16 terabyte instances on a server. But this gives customers a lot of cost savings. So the first customer that we had to do this for, they did not have the rack space to use commodity 1U servers. It was not an option for them to add 2 racks worth of servers to their system. And so this is what we had to come up with in order to serve that use case. And it gives you, savings in rack units. You have less cooling, less networking, less physical space, less administration. And typically compute becomes more cost effective as it gets into larger core counts. And then just the chassis metal itself, how many power supplies you need, et cetera. These particular chassis are a little bit more expensive as a per chassis cost, but when you consider the cost of 5 other 1 or 2U chassis in comparison, it is cheaper at the chassis level as well. The other benefit that it gives us is better handling hotspots. So everyone has their own kind of standard of what they run at. But if you consider, as an example, a case where you're running 50% CPU utilization as kind of your baseline goal per server, and you had a hotspot that tripled demand, you don't have 150% CPU. You can't serve all of that. You become throttled. But if you had a server that was big enough that you had 5 instances on it, and you tripled demand, even on 2 of the instances, you still have 10% CPU still available, and you've served that hotspot to your customers. And just to be clear, this is not virtualization that I'm talking about. This is instances of Cassandra on a single OS. Right? Because virtualization, you over-provision, you waste CPU. You under-provision, you don't have enough CPU for the hotspot. But not necessarily if you have an extremely dense server, but you might want to consider, are you overpaying on burst throughput or on compute that you could make a savings by, if you have a hotspot that's only on one server, can you say I'm going to handle 1 hotspot per 5 servers and make a savings on your total infrastructure cost? All right, but now we're talking about having more instances than replication factors in the cluster. How do we handle the instance replacement at these more horizontally targeted clusters? It's a similar process. We still recreate the system key spaces by copying and then swapping the system local system peers tables. But basically, there's an extra step of reducing how much data, or we're expanding the search for data, and then we have to reduce what we found. So we recreate the system key spaces, we snapshot a number of instances in the same site, and then we use SSTable split by partition to say that we can address each of these pieces of data independently rather than at an instance level or at a cluster level. Split by partition is extremely fast because you're just seeking to where the partition starts and where the partition ends, and then you're copying that to another location, so it effectively runs at disk speed. And then you're able to just open that SS table for the individual partition, figure out what the clustering key is, use Node tool get endpoints and say, is this a piece of data I care about or not? And if it is, copy it over the network at disk and network speed again, or else say it's not something I care about and delete it. And then we use Node tool refresh, or I think the new thing is node tool import to load the data. And so this is, again, runs at effectively disk and network speed and is very fast for us. I think this is another use case that many existing clusters could use to more quickly replace a failed instance and reduce the impact to the application of the cluster. And then the other kind of thing that we do, this is more of a kind of a business and application side thing, but if we can only ingest 300 or 350 gigabytes of data per month, how are we getting to all these terabytes and terabytes of data? Basically, we're doing the same kind of node replacement strategy where we copy the data, refresh it, or split by partition, get endpoints and refresh it. But then we're importing the data into Cassandra in bulk in parallel clusters. And so there was one instance 6 or 8 years ago where we had a project deadline moved up and we had to import decades of data in a very short period of time. And so we actually spun up Cassandra clusters on 20 different laptops to run imports in parallel in order to copy the data that much more quickly, because in that case, it was an application driver bottleneck where a competitor's historian, we could only access in a single-threaded driver. So we had to use more conversion applications, and it was like, well, we're already doing this, we might as well use Cassandra instances and just convert 1 month at a time and then copy that into the new cluster. That was the easiest way for us to scale that. So yeah, thanks for having me. Are there any questions?
When you're doing monthly key space
Mm-hmm.
or vertical scale, normally when you add more columns, more keys, more tables, more key spaces, the performance of the cluster degrades
Mm-hmm.
almost geometrically. Do you know what it looks like for how many key spaces can you handle, for instance? What's the allocation of RAM and CPU look like when you're doing that on those clusters?
Right, so a big part of that depends on what the activity is on each of those key spaces. If you're actively writing to that hundreds or thousands of tables, that is going to have an impact because you're creating mem tables for each of those tables that you're ingesting data to. That's putting pressure on the JVM heap, putting pressure on disk, on compactions and everything else. For us, because we're able to convert the data and we're only loading to the current month, we're really only operating writes on 1 or 2 key spaces at a time. And mem tables, once they're flushed to disk, don't reallocate in the JVM heap until you have another insert to that table. So we have in our longest retention cluster, probably 250 key spaces, upwards of 10 tables per key space. So that's quite a lot of tables, but because we're really only looking at the most recent key space for inserts, that doesn't put a lot of pressure on the JVM heap. And the queries also, the data is stagnant on disk, so you're not really doing anything with it. You're not using any compute. And so we use pretty much the standard configurations, G1, GC, 16 gig heap, and a couple cores per instance.
Keep allocation the same at a 1 key space and a 250 key space if you're simply treating.
Mm-hmm.
If 1 key space is hot and the rest are cold.
Right, I mean, it's all on the same RAID array, so we don't have hot, cold storage. I mean, it's also not supported in Cassandra yet. But from a heap perspective, yes. Yeah, I mean, the SS tables are open on initialization of the instance, but a lot of the other stuff, it's kind of just idle.
Is there any impact to the read on, are you doing write-heavy compaction on that, or?
Yeah, so because we're splitting it up kind of like time with the compaction strategy, that puts a cap on how much compaction will actually happen on that data. And so we use size-tiered compaction strategy as the default configuration and then just run a manual compaction at the end of the month. And that's basically going to limit it as much as you can. And like I said, restricting how many SS tables are considered in that read path also gives you a good savings on latency.
Totally going to rip that off by the month. So thank you for that.
Awesome.
Money I'll make doing it.
Yes?
It is a common problem.
Mm-hmm.
Related to this, I was thinking
Mhm.
Would that be something that would be helpful for you and solve the need for having key spaces for monitor, things like that? Maybe it can also be expanded in such a way that you can also automatically decide if you delete the oldest data if there's no space or something like that. Is it something that we could implement in Cassandra? Would it be useful?
I think in most clusters that would work. The kind of the two things I think about is we have one customer, or at least one customer, there's probably others I can't think of, where they have uneven retention policies based off of data center. And so we actually need to use key spaces to say this data center is RF0 and this data center has the full replica. Because operators don't need as much context as decades of data. They really only need a couple of months to a year or two. But corporate report, planning out improvements to the hardware in the field, you're doing kind of more deep analytics on that, and you need a longer retention of the data in order to serve those queries. The other thing is, kind of like I talked about, because we're partitioning at the key space level, we're reducing the number of SS tables in that read path because, time window compaction strategy is partitioning those windows on write time, whereas we're partitioning on the actual data we're looking for in the query. I think in most cases, yes, but we have some data that has to be, of course you can modify your write time as you insert data, but we have a number of cases where either the device in the field becomes disconnected from the control center, or there's an interruption to the Cassandra cluster or something like that, where we're ingesting data that's months in the past or something like that, or we're consolidating systems and yeah. Mm-hmm. Anyone else? All right. Let's see, I guess, how much time do we have? I guess filler content or call it? 1 minute? Okay. All right, I guess I'll end it with a hot take of, I think there's also a recommendation that you put your commit log and your data directory on different partitions or different volumes. I think it's unnecessary. At least if it's SSD. If it's hard drive, yes, absolutely, put it on different partitions, but SSD, one RAID array, no problem. All right, thanks for coming.
Hello, everyone. My name is Jung Liu. I lead the product marketing and strategy team at Wiz, where we help over 40% of the Fortune 100 secure their cloud environments. And I'm really excited to be speaking today about securing multi-cluster Cassandra and Gen AI deployments. So a little bit about the problem that we consistently hear from our customers from a security standpoint. We'll cover a little bit about the anatomy of what a cloud attack looks like these days, how organizations can detect those types of attacks and prioritize those risks ahead of time, so they're proactively removing those attack paths into the cloud environment. And then we'll move into my favorite time, which is actually demo time. And then we'll close with a few best practices for how organizations can think about building security earlier into the development pipeline, as well as cloud operations. All right, so a little bit about the challenge. So what we consistently hear from our customers is that cloud has represented a fundamental transformation for their security teams in 3 key ways. The first is that the environment is very different. Right? It's incredibly decentralized these days. And organizations very quickly find themselves in a multi-cloud, multi-architecture environment with thousands of technologies running in it. And there's a very simple question. What do I have running in my cloud environment? And unfortunately, it's a very complex question to answer simply. The second key thing is the risks themselves. What we hear routinely is I have all of these different tools and technologies that are in place, but they show me siloed views of my cloud and siloed views of risk. I'm getting thousands of alerts coming at me from all of these different tools. How do I prioritize what's actually real and eliminate the noise from these alerts that are meaningless? And lastly, what is actually, I think, the most important change is that the ownership model is very different. Right? It's no longer security teams or infrastructure teams themselves that are making technology choices. It is the business units. It's the development teams themselves. And so how do we actually ingrain a security culture into those teams? And how do we bring them in so that when we find an issue in our cloud environment, they are willing to help us fix it quickly? Now, this is one example coming out of AWS reInvent a couple of weeks ago that really articulates the problem statement. AWS is releasing all of these new incredible APIs all of the time, right? It's an explosion of features that allow us to build faster and build more innovative solutions for our customers. But all of that introduces more attack surface as well. And nowhere do we see this more right now than when it comes to cloud AI services. Based on the Wiz research team's analyses, over 70% of cloud environments are already using some flavor of AI in their cloud already. Oftentimes, it's a lot of R&D teams, a lot of innovation teams that are testing out new solutions, right? New use cases that they can roll out to customers. But what we also consistently hear is that security is oftentimes the main AI adoption blocker from bringing those new solutions to market, to actual productization. And again, it's the same themes. The technology itself is rapidly innovating. AWS just announced a whole slew of new innovations for Bedrock, their service for this. There's a lot of new risks, right? This was, I think, the fastest that an OWASP top 10 has been created for this area. And a lot of this is unknown risks as well. There's a lot we have yet to learn. And lastly, there's a security knowledge gap. Because now we're not just talking about our usual teams that are building in the cloud, we may have new teams, data scientists, AI engineers, that they themselves are new to this space as well. And we need to help make security very, very simple for them. So let's talk a little bit about the anatomy of a cloud attack. Exposure is still the key risk in cloud, right? In cloud, everything is born with an IP address, and so exposure is incredibly simple. And there's a lot of different ways that it can happen. A publicly exposed bucket, for example. What we found via our research is that if you expose an S3 bucket and you reference it in a GitHub repo, from the time that that gets published and it's exposed, it's really a matter of 7 hours until that's taken advantage of. A little longer if you don't expose it via GitHub with 13 hours, but still incredibly short. And these are not just, small names of organizations that are getting hit with this. It's really large organizations, the cloud providers themselves. You can see that with Amazon, you can see that with Microsoft here. And on the topic of AI, there was a fairly large accidental exposure recently by the Microsoft AI team, really showcasing the fact that all of this is very new, and yet a simple misconfiguration can lead to the exposure of 38 terabytes of data. Now, when we look at attacks, there's the simple ones, right? Simple exposure. But why is it so difficult for us to find these ahead of time? The reality is that oftentimes a lot of the attacks are a combination of different risk factors. And what we see is first, when an attacker gains a foothold into the cloud environment, they then look for ways to break out of it, right? How do I expand what I have access to? How do I find where your crown jewels are so that I can exploit them or steal them? And so there's a lot of different initial entry points into the cloud environment. There's, of course, remote code execution that we all know about. Log4Shell is one of the most painful recent examples of that. But we also see other factors as well, right? Misconfiguration of resources, which was the AI example that we just looked at. There's, of course, end-user compromise, oftentimes one of the weakest links in the chain. And we saw this with Lapsus, a group of really high school students targeting the likes of Okta and Microsoft and succeeding. And then, of course, there's also what we may unintentionally see in our attack surface, which is things that are introduced via our software supply chain. SolarWinds is a great example here. And also through the identity side, when we make identities available to third parties, as we saw with Nobelium. But once attackers get that initial foothold, what else can they exploit? And there's other different risk factors that they're looking at, right? So there may be secrets that are leaked that allow them to move laterally in the environment. It could be internal network connectivity or identity routes. We see a lot of excessive permissions that are out there, and unfortunately, weak authentication as well. So the combination of these two factors really enables attackers to gain that initial foothold and then grow their presence in the environment until they find what truly matters to an organization. Now, I wanted to walk through an example of what this looks like in real life. This is an attack that our research team looked at, which we call Quick Cow. And what we have here is a patient 0. This is an EC2 instance, right? So it's our virtual machine, and it's vulnerable, right? So it's got a vulnerability on it, and it's publicly exposed to the internet. And attackers are scanning cloud environments now, looking for this type of initial entry point. Now, once the attacker is in, right, they've gained that foothold, what do? So they immediately run a reverse shell. They deploy Dirty Cow, which is a known piece of malware. And from there, they see that there are 4 keys on this virtual machine. And they start testing them. What does it get me access into? And so the first 3, right, doesn't go anywhere. But then the last key they find actually allows them significant access into the environment. It actually gives them the permissions to create an IAM user. Now, this is like hitting jackpot for the attacker, because this is what allows them to actually move outside of our patient 0, to escape, if you will. And this is what we mean by that internal exposure, that lateral movement. Because from there, they can move very freely within the cloud environment based on the permissions of that particular user. And in this case, again, they're making those enumeration calls out to the cloud provider to see, hey, what does this IAM user get me access to? And in this case, they find actually an RDS, right? So a data store that has sensitive customer information, and they exfiltrate it. Now, this attack really takes only just a matter of minutes. The attacker gains that initial foothold at about 8 p.m. at night. They start exfiltrating in the wee hours of the morning. And by, I believe it was 6 a.m. in the morning, the attacker has already posted on Twitter evidence of the database that they have now exfiltrated. So this is really rapid, right? And the key question is, why is this so difficult for security teams to find? And it's because it is that combination of risk factors that traditionally takes many different security tools to uncover. So what we want to do here is really think about how do we address this holistically in our environments. The first is to start thinking about attack paths, right? That full attack vector from that initial point of entry into the critical crown jewels of an organization, and the lateral movement paths that enable that. And security goals in themselves are to first be proactive. Let's identify these attack paths before they can be exploited and close them down. Let's remove them as paths that an attacker can exploit. Now, because the cloud is filled with these types of risks and filled with these types of attack paths, it's nearly impossible to remove all of them from an environment, especially as you think about all of the different layers of the cloud, the orchestration layer, and the workload layer itself. And therefore, the other piece is we need to ensure we have the right level of monitoring in place so that we can detect when this attack is happening and actually limit the blast radius before the attacker gets to the crown jewels. Now, it's not just a technology problem. It never is. It's actually, more importantly, a people and processes problem. For too long, securing the cloud environment has really been seen as the purview of the security team itself. And that doesn't work for the speed and scale of the cloud, especially with that change in ownership model. And so what we believe is that not only do you have to have a transformation in how you think about risk, but you also have to think about how this new operating model that spans teams, one where the security team is really looking for visibility into what's in my environment, but the ownership and responsibility for risk itself ultimately lands on the development teams, right? So a dev team A that's responsible for one application, another dev team that's maybe responsible for a different environment, and then an AI team that's innovating rapidly with Gen AI. So how do you want to do this, right? There's a few key steps, 4 key steps that we want to make sure we put in place. The first is we want to identify risks with cloud context. That means really understanding, layered on top of our cloud environment, where we have misconfigurations, where do we have vulnerabilities, right? Combination of which can create that initial access point into the cloud. But beyond that, where do we have things like excessive permissions, exposed secrets, things that enable that lateral movement to the things that really matter in the environment. So in this example here, we've got our Cassandra cluster here in the center, and we can see it's got a public routing to the internet via this network interface, this virtual network, and this internet gateway. And in addition to that, it has a critical network vulnerability with a known exploit. So those two things in combination mean that this is a high probability of being compromised, right? That's that initial access point. But beyond that, we can see this cluster can be accessed by this role, which has excessive access, which also has access to a data store that's used for AI training that we know has actually sensitive data on it with personally identifiable information. So this second piece is that lateral movement path that gets you to those crown jewels. Now, once you have all of that information, you can really understand that this is a full attack path. And this is something that your teams can prioritize, right? There's no question that this is something you want to resolve before an attacker takes advantage of it. Now, the next key step, and again, one of the very complex questions around cloud security is who is responsible for this part of my environment? And you have to understand, in many organizations, this can be extraordinarily difficult, especially if you are a large global organization, right? You have different teams that have different environmental ownership, that have different application ownership, that have different data ownership. So you need to understand, how do I get this issue, this security risk that I found, to the team that is responsible for remediating it as quickly as I can. And from there, we need to automate the workflows, so working directly with the technologies that that team is already used to using. So if they might want a Jira ticket open, they might want a Slack message, right? Whatever it is that they use, you want to push it into that workflow so that that enables them to be armed with the information to take that immediate, fast action. All right, so with that, we're going to move into actually a demo of the solution. So what I have here is that full attack path that looks at a Cassandra cluster here in the center. And we can see that it is actually publicly exposed to the internet if we zoom in. Got this network interface, this load balancer, and we can actually validate that in fact there are these endpoints that are exposed to confirm it is publicly exposed. And we can see on this cluster there's a couple of CVEs that are associated with it, right? So CVE 2023, this has to do with vulnerabilities and misconfigurations. And then also this 2021 one, which looks at privilege escalation from Cassandra itself. So again, this combination of factors means that this is a potential entry point into the cloud, into this Cassandra cluster. But it's not just that. In this case, we can also see we have an identity, or this role, that has access to Cassandra. And in many organizations, with typical setup that we see, which is unfortunately a misconfiguration, is to have that same role also have access to the bucket, which is actually the backup for Cassandra, or for the production environment. Now, what I also want to show you here is the full lateral movement path. So building this out further, if we look at this bucket itself, we can see that we are finding sensitive data on it in the form of credit card information. And we can take a look and see exactly where it is in that bucket that we're finding it. But what's important is also that this bucket can also be accessed by these 3 admin accounts over here. So if someone were to compromise this Cassandra cluster that we started with, they would be able to move laterally in the environment through to this bucket and then into these admin roles for our cloud environment. So there's lots of different crown jewels that are now at risk. And what's also interesting is there's a second attack path here, which is we have this bucket. It's actually also misconfigured. It's available to the internet because it was misconfigured with the all users group, which in this case actually means all users that are logged into AWS, not just the users that are part of your organization that are logged into AWS. And so if someone actually breached this bucket, they would find a key to AWS, which allow them to assume this Okta SSO user in your environment, which can assume this IAM role, which can then get them also to these admin accounts. And as we saw earlier, these admin accounts can get to that Cassandra backup data. So now you have 2 routes into Cassandra, right? The one where Cassandra was your initial cloud entry point, and another one where something completely unrelated to what you're working on is actually the initial entry point. So it's really important to understand all these dynamics because these are different teams that own these different parts of the infrastructure that may not even be aware that these relationships and interconnections are in place. And that's what we mean by really understanding those full attack paths so you can prioritize removing them from the environment. All right, so I'm going to move into AI because AI is top of mind for everyone. What we believe, again, is very similar to cloud. It all starts with visibility, knowing what you have in your environment, right? So here you can see all of the different services. We've got AWS Bedrock, GCP Vertex, right? Those are the latest AI innovations from the cloud providers themselves that are hosted. And then, of course, you may be using the underlying components as well. We've got Hugging Face, Llama Index, phenomenal naming by those folks. But again, what we really want to understand is actually, where do I have the greatest risk in my environment? And this is one example for AI, and specifically for AWS Bedrock, where we're looking at a S3 bucket that holds AI training data. And you can see that an AWS Bedrock model is running on top of, or is reading the data from this bucket in order to run your model. Now, what we're also seeing is that this bucket is publicly exposed to the internet, and you can see the application endpoints and what is actually being shown when an attacker comes in. And again, what we see is not only can an attacker gain access to this because it's publicly exposed to the internet, but because of the way the identities are configured, which is actually a fairly complex exercise in AWS, with these IAM bindings, if an attacker got into this first bucket, they would be able to move laterally in the environment to get to another bucket. And again, canonical issue where you have a bucket that has a secret key that enables access into an IAM user that can assume a role that can then get to some really critical keys to the kingdom admin accounts in the environment. So this is what we mean by, again, really showcasing the full attack path into your Gen AI deployment, something that you may not be aware of. And what's really important when it comes to Gen AI is, in many ways, we can learn from what we learned from cloud, where security was really a backseat passenger into the innovation that was happening. With Gen AI, we need the seatbelts now, and we can co-develop it in collaboration with each other by adopting that new operating model. All right, so with that, I wanted to close on a few best practices that we've learned from our customers. The first is that you really need to think about, how do we make cloud security self-serve to all the teams, right? To our data teams, to our teams running Cassandra, to our teams building AI applications. And the first step is, it all starts with visibility. It has to be the same visibility across all teams and across the entire environment. So whether you're deploying on AWS or Azure, whether you're using Bedrock or OpenAI, we need to normalize it and make sure that everyone has the same visibility. As part of that visibility, we need to have full understanding of what applications are there, what are the pipelines, where is the data, what data of that is sensitive, and most importantly, who owns each of those, right? Who owns that part of the infrastructure, that part of the pipeline, and that part of the data? From there, once we understand the risks to the environment, we have to use context, right? Context about the teams that own it, about the cloud environment, in order to prioritize ruthlessly. And from there, it's a group effort to remove that risk proactively from the production environment to get to zero criticals. It's actually possible when you focus on what truly matters and not the thousands of meaningless alerts that most organizations get. And in that process, what we find is that we start to see the trust form between the security team and the dev teams. And this empowers developers to actually be proactive, right? When they see an issue, when they see a risk in the context of the cloud, they know that it matters, they feel the ownership, and they want to remediate it and take the right action. And lastly, the key is all about knowing what controls matter for your production environment. As you clean that up, you establish that. And through the trust that you have with all of the teams, you can get everyone on the same page about now extending those same policies, those same controls that work in production into the pipeline. So you're not just playing whack-a-mole in production, but rather removing entire classes of issues in the pipeline when it's much cheaper and easier for it to be resolved. Now, one of my favorite stories is from Priceline. They are a heavy Cassandra user, right? They have a lot of data that they need to process in real time. And I love the way that their cloud security architect frames it, right? It's guardrails. I like to think about guardrails in the same way as F1 races, right? Developers are our F1 drivers. We don't want to slow them down. We want to put seatbelts on them. We want to put the railings on in case something catastrophic happens. And this is really how we think about security done right for multi-cluster Cassandra, but also Gen AI, right? How do we give these teams autonomy to deploy securely and move faster in what it is that they're doing? Because ultimately, that has the largest impact for the business. All right, thank you very much for the time. Really appreciate it and hope this was useful. Thanks.
at 5 p.m. I know it's maybe we're the last talk between now and going to the bar, but thanks for coming. And thanks to the entire team for building this. We are just here to kind of representing a large team at US Bank who built this, and then a couple of them are in the room. And then thanks to the Cassandra team and the DataStax team also for kind of supporting us. So what we'll be going through is some of the cool mysteries that you guys have is when you swipe your credit card at a Starbucks or something like that, and then how does the transaction actually show up in the mobile app or a web app? Maybe we'll answer that questions and then partially at least. So I myself am Seshu Gudanti, Senior Director of Software Engineering at the US Bank, and then Venkat.
Hi, so thank you for coming and thank you for showing interest for the session today. I'm Venkat and I'm an engineering leader at US Bank with over a decade of experience. So most of my experience lies in the data space, data engineering, moving data between systems. And so my journey evolved from using leading ETL tools from the market, for the batch data movement, to a developing of a homegrown software platform at US Bank, a software product, enabling real-time data transfer. And I have delivered impactful projects for the bank, and today migrating workflows from mainframe to Cassandra is one of them, which is our topic of discussion today.
So just few words about US Bank and then the scope and scale of the problem that we solved. So the problem that we solve impacts consumers, and then consumers are part of the consumer and business banking. And we offer for consumers products like checking and savings and deposits, and then and loans. And then for credit cards also, which is the payment side of it, we offer credit cards. And then wealth management based on your net worth, then we offer different kinds of services. So if you kind of total up all of the percentage of kind of revenues, 80% of the bank's traffic is kind of impacted by the consumers space. And then the solution that we kind of built is for a large scale of the customers. That's on the sort of the scale side of it. And then the other side of the equation is the sort of the digital interactions are kind of increasing at a high scale or percentage points. If you look at it from 4 years ago to now, they went up by 16% on the digital transactions, and they went up by 20% on the remote deposits. And then it's not that somebody is actually encouraging them to kind of move to this digital. It's actually this trend of migrating towards digital is across industries and across many different companies. And then I'll just go over some of the drivers on why actually this digital transaction or the digital interactions are increasing. So one of the main reasons is that if you kind of look at it, as we are all moving away from the analog version of it to the digital version, the number of interactions actually will go up. So for example, if you were renting a DVD in the olden days with a DVD in a Blockbuster, you would browse for 20 minutes there and then check out one DVD and then return the DVD after 3 days. You would probably have 3 rows in the database, one for checking it out, one for returning, and then one for some late fee. So if you add up, maybe 3 transactions. But the equivalent of that, if you are kind of browsing on a Netflix, you'll browse for 30 minutes, and then you'll probably create, I don't know, 50 interactions or even 100 interactions on all the movies and the reviews, and then who the actors are. So you'll do a lot many interactions. And then even same thing with Kodak too. I mean, like if any of you remember the old film rolls, you would have like 24 or 36. But in the camera or in the iPhone camera world, people take like hundreds of pictures. So your kind of scale of interactions, the same concept, even same in the bank too. You don't visit a branch as many times. If you have a digital app, we would see like 10 times more transactions. So that trend is the one that is actually kind of impactful to the kind of existing infrastructure, which is kind of mainframe. So we have to move to a different infrastructure which will support a different scale of the interaction. So that's the first problem. And the second problem is that when customers are actually moving away from the digital transactions or from the analog to the digital, people want continuous engagement. And when I mean continuous engagement, again, if you go back to the old days of ordering a cab versus Uber, when you called a cab, you would probably have one kind of interactions. But when you look at ordering Uber, people follow that every turn by turn. Oh, it's 1 minute away, 5 minutes away, 10 minutes away, and then you keep track of it. So similarly, when we kind of wire money, when we do credit card processing, people are constantly following those transactions. That means that the number of interactions that they're going to have is significantly higher than in the traditional days. And the last thing is more on the velocity. So as we are developing more products and more features and selling them as bundles, there's a need for different groups to develop in parallel. And especially in the kind of the mainframe world, it was much more difficult for multiple teams to kind of operate. So we wanted to kind of unleash the kind of the creativity of all of the product managers and engineers. So we wanted many different teams to work on this. And this was another driver to kind of migrate away the workloads from. And I'm not kind of discounting the fact that cost is a driver, but there are other reasons to kind of move away from the mainframes. So I'll go into the simple kind of the architecture kind of view of this. It's a very simplified view. So from a UI, there is a UI meant like it could be a mobile app or a web app or even a customer agent, a generalized version of UI. And then somebody's making a address change, and then it goes through a thin domain layer, and the domain layer is nothing but a security. There are no business rules in it, and it goes to the mainframe. And mainframe has all the business rules, and then of course it returns back the data to the UI. And there from the backend itself, there are other batch updates that happen, batch or even real time, like credit card processing or ACH transfers. So all of them put together are sent back to the UI, which is about read transactions. So this is a very simple kind of representation of the architecture. And then if you want to move away from the mainframes, what are the strategies that we typically have from this world? One is we started moving away new domains or anything new, and don't put them in the mainframe anymore. Well, that will take care of, I don't know, some percentage of the avoidance in some sense that you're not building anymore. And the second one, which is probably the key part of the problem, is the read part of it, which is in a financial services especially, you don't wake up every day and then do transactions. Every day you wake up and mostly look at the transactions, but rather than modify them. So our kind of ratio to read and write is around 20 to 80%. 20% for write and 80% for read. So that's the focus of this conversation, and how we kind of migrated away the reads from the mainframe. And then, of course, we can move the non-core functionality. So all of these efforts are going on in parallel, but the one that we're talking about is the migration part of it. And then we could migrate the core, which is probably the most complex one, and also expensive. So as I said, for this particular conversation, we're talking about the read part of it. So now what did we do to achieve the reduction in the 80% of the traffic? And then we described the scale of the problem before. For 80% of the business is mostly consumer focused, and then 80% of that is read focused. So this forms a particularly significant chunk of the bank's problems. So again, starting with the left-hand side, this is the same architecture that I showed you before. So what did we do to that? So we modified the mainframes to put in a publisher So we can kind of answer why not CDC, but we modified the mainframes to publish the data, a full-fledged event, and then the events were published to a streaming platform. And the streaming platform consisted of an API abstraction on Kafka, and then of course Kafka, and then there was a event processor, Spark, and then all of this, a combination of that, which was built as a platform so that we could stream all kinds of data. We had around 40, 45 events or 50 events just for one kind of particular project. And then all of that, we moved it to Cassandra. And then we built some of the business rules now in the new domain layer. And then not only this, when we moved the data to Cassandra, you had an opportunity to kind of enhance the data. Like today, when you go to your credit card transactions, all of them are enhanced in what it was actually years ago. So some of the enhancements, enrichments happened, and then we built different kind of services too. You can search, you can do voice search now on the data that's there in Cassandra. So you can build a lot more features. This is what we did. And so now we are going to go into this particular CDA pipe and what we did at the mainframe, and then tell you some of the problems and challenges that we had. So there are like numerous problems that we encountered. Let's not be, and then here we are only listing some of them. Of course, the new system, whatever we built, the pipe, the Cassandra, all of them have to be reliable. They all have to scale, and we will go into like 3 of them because in the best interest of the time. So the first one that we will get into is the data transfer. For this whole thing to be kind of meaningful, when the event actually happens in the mainframe, for reaching the Cassandra, it has to be less than a second. And the reason why that is kind of important is, if you change an address in the mainframe and you want to go back and then see the address, you want the address to be reflected there. Same thing with transactions. When today you swipe the card, it would have gone to the mainframe, and then customers would kind of immediately look at it. And then if the data is now in Cassandra, and even if there is like a 10 more seconds delay, you are kind of degrading the customer's experience, what is today and what's what we are going to propose, or what we proposed, or what we did. So in that sense, like we didn't want too much of degradation of what the customers actually have today. And the next one is missing events. We are a bank. Even if the one transaction is gone, customers call you. Even if it's 1 cent away, people are going to call us. So we wanted to be very, very careful, and then build systems and processes to kind of detect the missing events. And the next one is there are potentially problems in the events even not being published. The mainframe itself could have problems, or maybe there's some business rules that kind of failed, and then events. So we had to have kind of some reconciliation between the mainframes and the Cassandra, run at a frequency. So we will get into the details on some of these problems and how we solved. And then Venkat, you want to go ahead and talk about these?
Right. Thank you, Sheshu. Okay, so the 3 problems that Sheshu was talking about, latency, right? Without bringing down the 1 second latency, this project doesn't exist. So we have done a number of performance tests. We can see we had more than 500 today. So the first thing is, how do we reduce? Where is the latency, right? So we started with the mainframe. So of course, Shesha mentioned CDC. There are reasons why we do not use CDC is one of them, right? So the mainframe, they tuned the number of threads, how many threads are listening to the events. They added, more, listeners, kind of more partitions when you talk about Kafka. That reduced the latency under 500 milliseconds within mainframe. So that's one part of it. There are a number of tests we have done, but so that's one of them. Then when mainframe published to streaming engine, of course, this is based on Kafka, Spark, and there is a Spring Boot, which is a REST API gateway for mainframe to publish. So it's a complete abstraction for mainframe. So they just published an endpoint. Everything was taken care of behind the scene. So the streaming engine it's probably processing in less than 100 milliseconds today. We started with the 1 second, more than a second. It was taking more than a second when we started with the Spark traditional D streams, which is a micro batch streaming. So it was taking more than 10 seconds. That's where we started when we started this journey 3 years ago. So of course the Spark structured streaming came in next, and continuous streaming is one of the part of the structured streaming. That helped us. You're processing every event, one message at a time. That also helped us to reduce the latency. And of course, Kafka, how many number of partitions you need to have the right number of partitions to speed up. So that's, using the right number of partitions, we'll also bring down the latency under 100 milliseconds. That means the moment you hit the streaming platform, the streaming box right here, we're taking 100 milliseconds, less than 100 milliseconds to write it to Cassandra. And the other important was checkpointing a destination. Here our Cassandra is the destination. And a Spark comes up with the fault tolerance. It comes up natively, checkpointing to some Hadoop system or some NFS. But it's an external system. So Cassandra helped us. One of the Cassandra features is atomicity. So you can batch your transactions. You have the data row, you have the checkpointing, and you have, there's another table called journaling. I'll talk about that in a bit. So you can batch it and write it to Cassandra. It provides very the high write throughput when you do that. So with that, we were able to bring down less than 1 second latency. There's one more thing with the checkpointing. We modified some of the native Spark code that gave us full control of our checkpointing. When you want to go back and replay those events, we are not dependent on Kafka. It's completely decoupled. So you can always go back to Cassandra, update your offsets. It's going to replay the events. So that's the important problem that we had to solve. And moving on to the two problems was data loss. So data loss is, just to give an example, you go to UPS and ship a package. You'll be worried about, hey, did my package reached? So that's why UPS gives us a tracking number, and we have that, confidence. We go and track that, and then when the message is delivered, you see the tracking number is updated. It's the same concept. So if you see that box journal, when mainframe publish any event, they track it. It doesn't cost anything. It's just a tracking number. They're not storing the entire payload. It's just a journal table with the tracking number. And then when the tracking number pass along with the streaming pipe. So when you write to Cassandra, we also store that tracking number. It's a short-lived, 3 days. We kept it for 3 days because you will come to know if the events are missing within the next 30 minutes. So what we built was, again, using this Spark, the streaming. It's not a streaming, it's a time interval batch pipeline built on Spark. Just checks every 30 minutes. You can, depending on your criticality of your data, you can change it to even 5 minutes, right? So what it is checking is finding out any mainframe published 1 million events. Did 1 million events reach to Cassandra? It doesn't do any data validation. It just identifies there is a data loss. Humans, we make errors. So I know we have all of the alerting enabled today, but when something fails, humans make, okay, he missed to address some of those, events. So that usually missing a transaction in Cassandra is a big deal for customer. If it doesn't see a transaction, it's a big deal for customer. So that's, data loss. Now, if you look into carefully the box, between mainframe and publish, there is an arrow, right? So when you change an address, mainframe itself never published the data to streaming engine. Data loss doesn't tell you that because the data loss doesn't know the event never happened. So that's where the next problem that we need to solve is data reconciliation. How do you know now the writes are happening in mainframe, reads are happening against Cassandra? How do you know the data is in sync? I know we have done all the quality testing, thousands of test cases. Every test case is validated in the lower environments before you move it to production, but they're always edge cases. So as long as we're using computer systems in the world, there will always be problems. So you need to be ready for that. So data reconciliation is an edge cases. So this is a capability. It's a product. It's one of the transformations. Think about the software platform we built it. This is kind of a transformation where you can plug it into your pipe to verify the data between two systems. So this is where the mainframe on the left side, mainframe is publishing the data. And keep in mind, we are not putting burden on the mainframe. The whole model is to reduce the cost on the mainframe, reduce the misuse on the mainframe. We did not put a burden. Like any company, everyone has data lake. So it's the same concept. Mainframe is sending the data to a data lake. It's a day-1 data. That's fine. So, but we use the data lake. We use the every element and column that is published in real time. So built a daily reconciliation pipeline. What it does is identifies 3 things. If you change an address, but mainframe never published that record into streaming engine, so it identifies as a missing record. Hey, there's an address change record, but it doesn't, Cassandra did not get it. Another one is mismatches. So the rows and columns are compared in this. It's a very fast utility that we built, so it can process millions of records as well. So the mismatches is something, again, you updated your street number, but Cassandra mainframe did not publish it. So that's one of the problems. But the problems could be anywhere, right? In streaming engine, in Spark, there's a memory loss that happens. Any events that get lost, data reconciliation is another control process that could identify proactively all the issues without impacting the customer experience. So with that said, the key takeaways are, 3 years ago when we started the real-time US Bank, everybody thought, hey, this is impossible, that you're going to do it in 1 second without impacting your customer experience. But it is possible with using the right technology. Of course, Cassandra, Spark, and there are other tools. I'm not saying Spark is the one, but Flink is another one that could be, potentially we could even use Flink for the real-time going forward. But we have Spark built with both batch and real-time components, so it is solvable. And so latency is one of them. We solved it, less than 1 second. It's better than that. I would say most of the 95% of the messages are under 500 milliseconds between mainframe and Cassandra. So I would say thank you for everyone being here, and thanks to DataStax and Cassandra giving this opportunity. And of course, thanks to the team in the ES Bank, the entire team who helped us, who encouraged us, all the leadership. So thanks to everyone to make it happen. And I'll open the floor for any questions.
Sure.
So did you migrate only the messaging part or even the DB data table? Did you migrate everything?
So we migrated the data, and the structures in the mainframe could be different from how we stored it in Cassandra, because the mainframe structures were probably best suited for its storage system on how it indexes the data or whatever mechanism it is. And then we stored in Cassandra the way the reads from the clients would be, like from the mobile app or the web app. So the structures could be different, but the data is the same.
Yeah, so the data, the model is not just one-to-one. The DB table is not one-to-one. So
in that case, this Cassandra store is targeting the mobile app and the upstream apps?
Yes. Yeah. Yeah.
Yes.
That's what I do.
Oh, okay. Any other questions? Sure.
You use Solar?
Yeah, so we use Solar. The simple answer is yes. The complex answer is relative to most of the use cases would be based on the key. We have a customer key and account keys, and then so you can actually retrieve when the user logs in a bank. At least we clearly know who the user is and what account they're kind of related to, so we can pull the exact data. But there are some edge cases or less percentage of the use cases where search is kind of needed, and search was provided. But for that, the latency is actually slightly more higher for the Solar to kind of re-index. So there's kind of difference. So we have to kind of carefully orchestrate the searches in such a way that the customers doesn't search, insert into the mainframe and search within the next second, and then it may or may not exist.
Some of the like not critical functionality like voice, right? So it's not customer is expecting, the low latency in that. So the Solar is used kind of voice in such use cases, but not in the, when you log into your mobile app and want to see transactions, it's all key based, provides the, the low latency. Yeah.
Yes, it comes with it, but there is a, if you insert into kind of Cassandra, then, of course, the data is there, persistent, but for re-indexing of the Solar or indexing of Solar takes few extra seconds. So that's not counted in the budget of 1 second. That's what I meant. So it may take 2 seconds, but yeah. Sure.
Just curious, what is your transactions
It's in the billions. Yeah. Billions. Yeah.
Right. I think the peak, it depends, right? The peak traffic, usually 300 TPS, during the business hours. So for the 1 second, I mean, 95, the way is, I'm not saying 95 percentile, but what we measured is if you have 1,000 messages in that second, 95 messages are, we proved that it is writing under 1 second. There's always spillover, right? And that we cannot, the spillover is not in minutes, but at least it's in, extra more than a second. So we have alerts enabled, anything above, less than 95, tell me why, right? So sometimes, mainframe might be publishing a little late. So, and sometimes it's in the streaming pipe, it's a little delayed, Kafka lag and all of that.
So, yeah, we have fine-tuned this over some few months, maybe even a year. And to Venkat's point, we have made sure that 99% of the 99% of the events, not percentile, 99% of the events are within the 1 second. And as we said, we kind of fine-tuned the number of threads on the mainframe to partitions to kind of the technology of the event processor to the checkpointing. So lots of effort have been gone there. So that's almost, without which, like as we said, there's no reason to build it. So we built it to make sure that we meet that.
Yeah. Sometimes it even matters Spark on VMs, which disk you're using. You're using SSD or for the garbage collection, all of that. Even if we went to that level, Spark is better if you use SSD, but not on the virtual disk.
So how regarding the reconciliation, right? How are you guarding that?
Guarding that?
Are you adding some bad data, unsecured data?
No, it's not the security concerns. Sometimes what happens is when the data gets written, I'll just give maybe one biased data point, but when you write to some of the mainframes, for example, the event doesn't get published. It could be whatever, maybe it kind of crashed or maybe not crashed, but we don't know the exact reasons, but let's assume it didn't write it. So the data loss won't catch it because nothing was actually published. But the batch export from the mainframe would have that record, and you will not have a corresponding record of that in Cassandra. Then we know that, hey, yes, the data recon. That's again what happens is when we kind of, when we went to production, say on day one, the data recon will produce, 1,000 errors. But you fix all of those edge cases, and then, now if you look at it, maybe you'll have 10. And then we constantly keep fixing it. And then hopefully there'll be a day when data recon is kind of not needed. But of course, we need that as an insurance.
So it's not for not all of your data is wrong. Think about that, right? If all of data is wrong, that is, you'll come to know immediately like that, right? So it's a subset of customers, right, is impacted. Maybe just one of the product that we offer, just making it up, money market. So if there's something wrong with the money market data, we know exactly how many customers have a money market accounts. And this could identify, it's like when you cook rice, right? You're not checking every piece of it. You just check like that. So it's the same thing. Data reconciliation is a sampling. So the moment you identify the issue, we can quantify what all the impacted customers, and then we can quickly react to it. So and it can proactively, can be fixed as well.
Good. So, I mean, that's not the, at least, I mean, this project is not driving that. But as we told that there are, new domains are being built outside. We are migrating the reads. The reason why the mainframes are far, or at least in the thought process wise, say we acquired another bank. The writes itself are going to go up. Yes, we kind of drained out all the reads, but the writes actually went up because we are actually doing more customers now. So the goal is not to kind of replace it, but augment it in such a way that we are actually kind of doing different kinds of services and also serving more volume or interactions to the customer, which were probably cost effective or less cost effective on the mainframe versus. So think of it as that way, and then maybe there is some future at some point where the core will be migrated, but that's not the kind of line of sight for us. Yeah, all the transactions that you swipe your card, ACH transactions, money movement transactions, and all of that. Yeah. Go ahead. You had a question?
No, that is the first question.
Okay. Okay.
All right.
Time's up apparently.
Thank you, everyone.
Thank you, guys.
Let's hit the happy hour.
Yeah.